Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the oldest and most beautiful dreams in science, the dream that everything, from the smallest flicker of light to the vast motion of galaxies, might be described by a single, elegant idea. It's a dream so old it was whispered by philosophers long before there were telescopes or laboratories. A dream that has inspired physicists, poets and wanderers alike, the search for a theory of everything. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the tiny constellations of listeners scattered across our planet, each glowing softly in their own little slice of night. Now, feel free to dim the lights, maybe turn on a fan for a gentle background hum, and take a slow, easy breath. Let the hum of the world around you settle, like dust floating down through a sunbeam. Perhaps imagine the faint ticking of a distant clock, a reminder that time still moves even when we pause to listen. And when you're ready, let's drift together into tonight's quiet journey into the story of our long and beautiful search for unity, for the thread that might bind everything in the universe together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. The search for unification began long before physics had equations. In ancient Greece, philosophers like Thales believed everything came from water, not because they thought the sea made people, but because they were trying to find a single origin for all forms of change. To them, unity meant simplicity, and simplicity meant truth. Later, the idea evolved into the concept of four elements: earth, air, fire, and water, which the ancients imagined could blend in different proportions to make the diversity of the world. Even in that early imagination, the yearning for order was already there. The feeling that behind all the noise of life, something must quietly hold it together. Centuries passed, and the dream persisted. In the 17th century, Isaac Newton took one of humanity's boldest steps toward that invisible thread. When an apple fell from a tree, Newton saw not just fruit but the echo of the moon's orbit. The same invisible pull that guided the planets also reached down to Earth, tugging at the apple's stem. With one equation, Newton wove together heaven and earth. His law of gravity was more than a formula. It was a promise that nature could be understood through unity. The falling apple and the circling moon were no longer strangers. They were dancers in the same choreography. But every unification also reveals its cracks. When Newton imagined gravity, he saw it as a mysterious force acting across empty space, instantaneous and universal. For 2 centuries it worked beautifully, until Einstein came along and asked the forbidden question: what if gravity isn't a force at all? What if space and time themselves are part of the dance? Einstein's theory of relativity was like turning the universe inside out. Instead of invisible strings pulling on matter, it said that matter bends the fabric of space and time, and objects simply follow the curves. The sun doesn't hold the earth by force. It shapes the road the earth travels along. The planets move not because they are pulled, but because the map of space-time tells them where to go. To imagine this gently, think of a bedsheet stretched tight, with a heavy marble placed in the middle. The fabric dips, and smaller marbles roll around it. That's gravity, not a tug but a curve. Einstein had turned geometry into the language of the cosmos, and yet, even Einstein knew his masterpiece was unfinished. While his theory explained planets, stars, and light itself, it couldn't touch the smallest scales, the jittering world of atoms and probabilities described by quantum mechanics. Einstein's universe was smooth and continuous, like a calm ocean. The quantum world was restless, granular, more like a storm of bubbles and waves colliding. Two visions of nature, both breathtaking, both right, and yet utterly incompatible. Still, the dream of unification endured. In the early 20th century, scientists began to wonder if all the forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, might be different expressions of the same underlying law. Each success in physics seemed to whisper, the pattern continues. Maxwell had already united electricity and magnetism in the 1800s, showing they were two sides of the same shimmering field. Later, quantum theory revealed that light and matter speak the same language. Both are vibrations of energy. Every discovery seemed to promise another thread closer to the final tapestry. But the more beautiful the dream became, the more stubborn reality grew. When physicists tried to weave gravity into the quantum fabric, the mathematics began to tear. Infinities appeared where there should have been numbers. Equations refused to balance, like instruments slightly out of tune. And yet, no one could stop listening, because within that disharmony was something hauntingly familiar, something that still hinted at unity. Perhaps the simplest way to think of the theory of everything is like tuning a symphony. Each instrument, each force of nature plays its own melody. Gravity hums in the deep tones of space-time curvature. Quantum fields shimmer in the high notes of probability. Electromagnetism, the strong and weak forces, all play their parts. But every time we try to tune them into one perfect harmony, some note drifts sharp, another goes flat. The music never quite resolves. And yet, that doesn't make the attempt meaningless. The beauty of physics, like the beauty of music, lies not only in resolution but in the tension that leads there. The search for unification is a reflection of our own desire for coherence. To believe that the universe, however fragmented it appears, has a single heartbeat beneath it all. If you were to stand under a clear night sky, away from the city's noise and look up, you might feel that same longing. The constellations don't truly exist. They're illusions of perspective, random stars joined by our imagination. But we connect them anyway, drawing patterns, naming stories, turning chaos into meaning. That's what science does too. It draws connections between distant lights until the sky becomes a map. And yet, as we'll discover, every map is temporary. Every unification gives way to new mysteries. Newton's gravity gave us orbits and tides, but it couldn't explain light bending around the sun. Einstein's relativity reshaped space and time, but faltered at the smaller scales. Each success carried within it the seed of its undoing, and perhaps that's what keeps the story alive. If we follow the thread a little further, it leads us to the modern age, to a universe where two grand theories, both magnificent, both true in their own realms, refuse to join hands. A world where space-time bends smoothly, but particles flicker and disappear, where the continuous and the discrete, the certain and the uncertain, stand face to face like old rivals. And between them, the dream of unification still hums, soft, distant, unfinished. As our quiet exploration continues, we'll step into that divide, to see why gravity and quantum mechanics, the two greatest languages of reality, seem unable to understand each other, and what their conversation might be trying to tell us about the universe and about ourselves. The 20th century began with a promise that the universe could be explained in full. The great clockwork that Newton imagined had run so perfectly for centuries that most scientists believed there were only a few loose ends left to tie. If you knew the position and motion of every particle, you could, in theory, predict the future like the turning of gears. The world, it seemed, was logical, measurable, complete. But reality had other plans. In a span of just a few decades, that neat mechanical universe fractured into two astonishingly different visions, both true, both breathtaking, and both unable to live under the same roof. One was Einstein's general relativity, a story of smooth space-time that bends under the weight of stars. The other was quantum mechanics, a strange new world built from probabilities, uncertainty, and invisible jumps. Together they became the twin pillars of modern physics, and the reason we still don't have a single, unified picture of reality. Imagine it like this. One theory paints the cosmos as a calm ocean, where every wave flows smoothly into the next. The other describes a storm of bubbles, each flickering in and out of existence, unpredictable yet deeply connected. Both pictures are accurate, but when you try to overlay them, they tear each other apart. It started, as revolutions often do, with something small. In 1905, a young clerk in a Swiss patent office wrote a series of papers that quietly redrew the boundaries of space and time. One of them, about the nature of light and motion, became the foundation of special relativity, showing that time could stretch and space could shrink, depending on how fast you move. Another proposed that light comes in tiny packets of energy, which we now call photons. That idea was the seed of quantum theory. It's strange to think of it now, that Einstein, the man who later challenged quantum mechanics, was also one of its earliest architects. But his greatest leap came 10 years later, in 1915, with general relativity, a theory so elegant that even today, over a century later, it continues to astonish. In Einstein's universe, gravity is not a force pulling objects together. It's the shape of space and time itself. The sun doesn't tug on the Earth, it simply curves the space-time around it, and the Earth, following the easiest possible path, moves along that curve. Space and time aren't separate entities anymore. They are threads of the same fabric, stretching and bending under the weight of matter. If you picture a sheet of fabric held taut and drop a heavy ball onto it, the fabric will dip, forming a shallow bowl. Roll a marble nearby, and it will spiral around the ball trapped in the curve. That's the Earth orbiting the Sun, a dance written not in forces but in geometry. The success of this theory was immediate and dazzling. When starlight passed near the Sun during an eclipse, it bent exactly as Einstein predicted. Time itself ran slower near massive bodies, as confirmed by experiments decades later. GPS satellites today must correct for this tiny warping of time just to keep your phone from getting lost. Relativity worked so beautifully that it felt like the final truth. And yet, around the same time, another revolution was brewing, one that would make even Einstein uneasy. In the laboratories of Europe, scientists were studying light, heat, and the structure of the atom. They noticed something unsettling. At tiny scales, nature behaved not smoothly, but in jumps. Energy came in discrete packets, or quanta. Electrons could only occupy specific orbits around the nucleus, and when they jumped between them, they emitted light of precise colours, a cosmic Morse code. Out of this grew quantum mechanics, a theory that said the universe, at its smallest, is governed by probabilities. You could never know both where a particle is and how fast it's moving with perfect accuracy. The more precisely you measured one, the blurrier the other became. This wasn't a failure of technology, it was a built-in feature of nature. Reality, it turned out, doesn't reveal all its cards at once. In the quantum world, a particle isn't a solid dot but a shimmering cloud of possibilities. Only when you observe it does it seem to choose a position. Between observations, it exists as a wave of potential, both here and there, both moving and still. To Einstein, who believed the universe must be logical and deterministic, this was intolerable. God does not play dice, he famously said. But quantum mechanics seem to insist that the universe not only plays dice, it sometimes hides the dice until you're not looking. The conflict between these two visions soon became impossible to ignore. Relativity describes a universe where everything is continuous, where cause and effect flow seamlessly like a river. Quantum mechanics describes a universe where things happen in leaps, spontaneous, probabilistic, almost magical. Relativity works perfectly for the large, planets, galaxies, black holes. Quantum mechanics works perfectly for the small, atoms, electrons, subatomic particles. But try to apply both at once, say, near the centre of a black hole, or at the first instant after the Big Bang, and the equations stop making sense. One theory says space-time is smooth and flexible. The other says everything, including space-time itself, should fluctuate. One says the fabric of the cosmos can stretch infinitely. The other whispers that, at some unimaginably tiny scale, a distance a trillion times smaller than an atom, space itself might come in discrete grains, like pixels on a cosmic screen. This mismatch is more than a technical problem, it's philosophical. How can reality be both continuous and discrete, deterministic and uncertain? How can the same universe speak two languages that can't be translated into each other? For now, physicists live with a kind of truce. They use relativity for the vast and quantum mechanics for the small, switching between them like travellers crossing a border. The problem only appears when the two realms overlap, where gravity is strong and quantum effects are significant, such as in black holes or the first fractions of a second after the Big Bang. There, the two theories clash violently, producing infinities where there should be numbers and paradoxes where there should be predictions. It's tempting to think of this as a failure, but perhaps it's something else, a sign that our understanding, while profound, is still partial. Maybe both theories are reflections of a deeper truth, seen from different sides. Einstein once wrote that the most incomprehensible thing about the universe is that it is comprehensible. But maybe what he didn't say is, equally true, that the universe is only partly comprehensible, and the rest, the gaps between our theories, is where imagination takes root. If we follow the thread a little further, it leads to a humbling realization. For all our brilliance, we may still be standing on the shoreline watching two great tides, relativity and quantum mechanics, rising toward each other across a sea we don't yet understand. And somewhere out there, beyond the waves, lies the dream of unification, waiting for someone, someday, to build a bridge sturdy enough for both worlds to cross. If you close your eyes for a moment and picture the universe, you might imagine it as a grand stage, a smooth, endless arena where everything that has ever happened is still happening somewhere, woven into a fabric called space-time. Every planet, every photon, every breath you take leaves a tiny imprint on that fabric. It stretches, bends, and ripples as stars move, as galaxies collide, as gravity hums quietly in the dark. That image of the cosmos as a curved, flexible stage is the gift of Einstein's general relativity. It tells us that space and time aren't separate threads, but part of one continuous cloth, like the warp and weft of a cosmic tapestry. The movements of matter and energy shape that fabric, and in turn, the shape of the fabric tells matter where to move. There's a kind of mutual conversation going on. You tell space-time how to curve, space-time tells you how to fall. But quantum mechanics, that shimmering other half of modern physics, offers a completely different picture. In its story, the stage itself begins to shimmer. The smooth fabric dissolves into something restless, uncertain, almost alive, like the surface of the sea where every droplet flickers in and out of existence. To the quantum mind, nothing is continuous. There are only probabilities and possibilities, clouds of maybes that only collapse into certainty when you look. It's not that nature is playing tricks on us, it's that observation itself is part of the act. The universe, in some deep sense, seems to need an audience to decide how it appears. Now here lies the tension. Relativity is built on smoothness, on the idea that space-time can be divided infinitely, that gravity is simply geometry. Quantum mechanics is built on discreteness, on the idea that energy, matter, and even information come in tiny, indivisible packets. Each theory is internally perfect, consistent, elegant. But try to mix them, and they rebel. Physicists often describe this conflict as trying to write a script where the stage directions keep changing, while the actors are still performing. In Einstein's play, the stage is solid. It bends and flexes, yes, but it's continuous. In quantum theory, the actors are unpredictable. They teleport, superpose, blur, and vanish. When you combine the two, the stage starts flickering along with the actors. The lines between them dissolve. Let's imagine you're watching two dancers on that stage. One follows a smooth, graceful waltz, slow, deliberate, predictable. The other moves in jumps, here, then suddenly there, unpredictable, but full of life. For a few moments their rhythms align and you can almost see a single choreography. But soon the steps fall out of sync. The waltz and the flicker refuse to merge. That's what happens when we try to make quantum mechanics and general relativity dance to the same tune. To see how deep the problem goes, consider what happens when we try to describe gravity, which is geometry, using the language of quantum fields. In particle physics, we describe forces as the exchange of tiny messenger particles. Electromagnetism, for example, is carried by photons. The strong nuclear force is carried by gluons. Each of these forces can be quantized, described as a set of probabilities where particles pop in and out of existence, obeying quantum rules. So physicists naturally try to do the same with gravity. If gravity is a force, maybe it too has a particle, the graviton. A delicate massless quantum of gravity that ripples through space-time, mediating the attraction between masses. On paper, it almost works. But when you actually do the math, when you try to calculate how these gravitons interact at extremely small distances, the equations explode into infinity. Every correction term generates another infinity and another and another. It's as if you're trying to count raindrops in a storm that never ends. This is what physicists mean when they say that quantum gravity is non-renormalizable. In softer words, it refuses to clean up. Most quantum field theories can sweep away these infinities by adjusting a few constants, a bit of mathematical housekeeping that keeps predictions finite. But gravity won't play along. It's too wild, too deeply tied to the structure of space-time itself. At first glance, that might sound discouraging, but it also hints at something profound. Maybe gravity isn't a force like the others. Maybe it's something deeper, the shape of reality itself, not just one more field floating within it. In that view, trying to quantize gravity is like trying to measure the ruler you're using to measure everything else. This is why gravity has become the quiet rebel of modern physics, the outsider at the family gathering of forces. The strong, weak, and electromagnetic interactions all live happily within the framework of the Standard Model, our best theory of particles. But gravity, elegant and ancient, remains separate, geometric, not quantum. And yet, despite that separation, physicists have found a small consolation. Even if gravity refuses to merge completely, we can still describe its quantum effects at large scales through what's called an effective field theory. In simple terms, it's a pragmatic truce. It says, we know gravity breaks down at some incredibly high energy, perhaps near what we call the Planck scale, where space and time blur together, but we can still use it perfectly well for everything below that. Think of it like using a detailed map of your city. It shows streets, rivers, and landmarks, but not the grains of sand or the ants crawling along the sidewalks, yet it's still useful. The map doesn't fail just because it's incomplete. it's complete for the scale it was meant for. That, in essence, is the story of modern physics so far. A patchwork of perfect maps, each valid in its own territory, but none yet capable of covering the whole world. And so, the great question remains, what happens when the smoothness of space-time meets the quantum flicker? What happens at the edge of a black hole, where gravity becomes infinite, or at the very beginning of the universe, where everything we know was compressed into a space smaller than a proton? There, the smooth fabric of relativity tears, and the quantum storm rushes in. Some physicists imagine that space-time itself might be made of discrete building blocks, tiny loops or networks or vibrating strings. Others think gravity might be emergent, like the surface tension of water, arising from deeper, unseen interactions. But one thing is certain: the universe refuses to fit neatly into our categories. It is smoother than we can quantize, and more restless than we can curve. It's a paradox that can be frustrating, but also strangely comforting, because it means the cosmos still has secrets left to tell. If we drift a little further along this path, we'll see how scientists, undeterred by these clashes, began to look for harmony again, in theories that tried to unify gravity with the other forces, to bring the outsider back into the fold. And though many of those attempts would stumble, each left behind something beautiful, a new way of seeing the same stubborn universe. The deeper scientists tried to weave gravity into the quantum picture, the more it slipped through their fingers, like water refusing to be contained by the net of equations. Every other force of nature, the electromagnetic, the strong and the weak, fit neatly into the language of quantum fields. They could be written in the same mathematical grammar, like different dialects of one underlying tongue. But gravity spoke something older, softer, and far less cooperative, the language of curves and geometry. Physicists thought, at first, that this might simply be a matter of translation. After all, it had worked before. When electromagnetism seemed mysterious, quantum electrodynamics gave it structure. When the nuclear forces appeared chaotic, quantum chromodynamics brought order. So they tried to do the same for gravity, to turn Einstein's smooth space-time into a quantum field that could ripple and interact like any other. The idea was elegant in its simplicity. If gravity is a field, then it should have a quantum particle, a carrier of the gravitational interaction, much like photons carry light. That hypothetical particle was named the graviton, a tiny massless ripple in space-time. In theory, these gravitons would swarm around massive bodies, transmitting the gentle pull we feel as gravity. But when physicists tried to describe these interactions in detail, a problem arose, not a small one, but a kind of mathematical avalanche. In quantum field theory, you calculate probabilities by adding up all the possible ways an interaction could happen. Each path contributes a number, and though the calculations can grow complicated, they usually converge to a finite result after a process known as renormalization, a careful trimming of infinities that appear along the way. Gravity, however, didn't play by those rules. The deeper you went, the higher the energy, the smaller the scales, and the more wildly the numbers exploded. Infinities piled upon infinities, like mirrors reflecting mirrors stretching to nowhere. Every time you tried to renormalize gravity to sweep away the divergences, new ones would appear, cascading endlessly. This is what physicists mean when they say gravity is non-renormalizable. It's a polite way of admitting defeat. The math won't tidy itself up. The infinities don't cancel. Gravity, at least as Einstein described it, refuses to become quantum friendly. In soft physical terms, it means that when you zoom in too closely, to distances smaller than what we call the Planck length, roughly 1/10,000th of a trillionth of a trillionth of a trillionth of a meter, space-time itself stops behaving like a smooth fabric. It begins to shimmer with uncertainty. Space and time fluctuate, twist, and blur. Trying to apply the neat tools of quantum field theory there is like trying to paint on fog. It's a humbling thought. Our best descriptions of the universe, the equations that predict planetary orbits and atomic transitions with breathtaking precision, simply stop working at the very edges of reality. Nature, it seems, draws a soft veil over its foundations. But as with so many scientific failures, this one revealed something profound. Physicists realize that maybe gravity isn't just one more field to quantize. Maybe it's something deeper, a sign that space-time itself is not fundamental, but emergent. In that view, gravity might not be a force transmitted by particles at all, but a kind of collective behavior, like the waves on an ocean that arise from the motion of countless molecules. Think of how temperature emerges. No single atom has a temperature. It's a property that appears only when many atoms move together. Gravity, some theorists suggest, might be like that. Not an independent entity, but a statistical whisper from the microscopic degrees of freedom that make up space-time itself. Still, that's not the whole story. Even if gravity resists full quantization, physicists have found a way to make it mostly behave within the quantum framework. The key lies in treating Einstein's theory as what's called an effective field theory, or EFT for short. The idea is delightfully modest. Instead of insisting on knowing everything, EFT says, let's describe what works within the range we can observe and accept that the theory might change beyond that. In other words, general relativity doesn't have to be valid at all scales to be useful. It just has to be accurate up to a certain point. Beyond that point, new physics takes over. The Planck scale becomes a kind of horizon for our understanding, the boundary beyond which the familiar laws dissolve. You can think of this like looking at a coastline from an airplane. From above it seems smooth, well-defined, but as you fly lower, the edges begin to fray. Tiny bays and rocks appear. Get closer still, and you see grains of sand, shells, and shifting water. Each level of zoom reveals new details, new patterns, and the rules that describe one level no longer capture the next. Yet that doesn't make the earlier map wrong. It's just a simplified layer of a much richer truth. Gravity, as an effective field theory, behaves the same way. At the scales we experience, from falling apples to orbiting planets, from satellites to galaxies, it works perfectly. It predicts everything with exquisite precision. But as we push closer to the Planck scale, the details blur. New degrees of freedom must emerge, perhaps strings or loops or some unknown quantum texture of space. In this light, the failure of quantization isn't so much a dead end as it is a signpost. It tells us that gravity belongs to a deeper structure, one that our current mathematics can only gesture toward. Like the faint sound of music leaking through a wall, it suggests there's another layer of reality just beyond our hearing. Some physicists believe that this deeper layer might eventually explain not just gravity, but why space-time itself exists at all. Others suspect the key may lie in information, in the strange equivalence between entropy, geometry, and the holographic patterns we find near black holes. But whatever the answer, one truth stands quietly in the background. Gravity refuses to be reduced, and perhaps that refusal is meaningful, because in a way it mirrors us, our own reluctance to be defined entirely by equations, our tendency to exist somewhere between certainty and wonder. Gravity, like consciousness, bends, but never fully breaks into the language we try to impose upon it. It holds the universe together, yet remains the most elusive thread in the cosmic fabric. As we drift a little further along this path, the story begins to widen again. If gravity won't merge with quantum mechanics directly, perhaps the solution lies in looking beyond, in reimagining what matter and energy themselves are made of. From that question arose a breathtaking new idea, that everything in the universe might not be made of point-like particles at all, but of tiny vibrating strings, the music beneath matter. And it's to that idea, shimmering between beauty and impossibility, that our next quiet exploration now turns. Among the four known forces of nature, gravity has always been the quiet one, patient, soft-spoken, and yet the most persistent companion of them all. It shapes galaxies, sculpts the flow of time, and decides the life and death of stars. And still, when we turn our microscopes toward the quantum world, it refuses to appear. It lingers at the edges, like an old relative who never quite fits in at the family table. In the standard model of particle physics, the grand framework that unites electromagnetism, the strong force, and the weak force, the universe feels neat and tidy. Each force has a messenger, photons for light, gluons for the strong interaction that binds quarks inside protons and neutrons, and W and Z bosons for the weak force that drives radioactive decay. Together, these particles dance through an intricate web of symmetries. The equations describing them are renormalizable, meaning they behave well when zoomed into the quantum scale. They form a complete and harmonious family, at least on paper. But gravity doesn't belong to that family. It doesn't share their symmetries. It doesn't obey their rules. It refuses to be described as a tidy quantum field living inside space-time, because gravity is space-time. It doesn't live within the stage. It creates the stage itself. Physicists have sometimes called it the odd one out, or even the orphan force. The standard model works beautifully for the microscopic world, predicting particle collisions with accuracy so sharp it's like measuring the width of Earth to within a single hair. Yet for all its glory, it ignores the thing that keeps your feet on the floor. Gravity isn't part of its equations at all. This outsider status isn't just a technical annoyance, it's a clue. It tells us that gravity operates on a deeper level, one that the quantum picture doesn't yet capture. To understand why, it helps to recall that the other forces are built on a principle called gauge symmetry. Imagine the universe as a vast field of invisible threads. The vibrations and twists of these threads create the particles we see. Electrons, photons, quarks. Change one part of the thread, and the rules adjust themselves everywhere else to stay consistent. That's gauge symmetry, a hidden order beneath the chaos, ensuring that the laws of physics look the same no matter how you view them. But gravity isn't like that. It doesn't need symmetry to be invariant. It simply curves space-time itself. Where gauge theories describe interactions within space, gravity describes how space and time themselves respond to matter. It's not a field living on a surface, it's the bending of the surface itself. This subtle distinction is why gravity resists being quantized in the same way as the other forces. When you quantize a field, you assume that the underlying stage, space-time, is fixed and unchanging, a kind of grid on which particles move. But in general relativity, that grid moves with the story. It stretches, compresses, and folds under the weight of matter and energy. In other words, you can't define a quantum of space-time without first defining space-time, and you can't define space-time without gravity. The logic circles endlessly back on itself, like a Mobius strip. Some physicists have suggested that maybe gravity isn't fundamental at all, that it could be an emergent phenomenon like temperature or pressure. No single atom has a temperature, but a collection of atoms does. Likewise, perhaps no single quantum field has gravity. But when enough of them interact, something like curvature emerges. In this picture, gravity isn't a law, it's a consequence. It's an idea both humbling and profound, because it suggests that space-time, that sacred backdrop of existence, might not be basic. It might be built from something deeper, perhaps from information itself, or from the subtle interconnections between quantum systems. In such a view, gravity would be the shadow cast by those hidden correlations, much like how a smooth fabric hides the countless threads that make it. One of the most beautiful examples of this perspective comes from black holes. When matter falls into a black hole, it seems to disappear forever, yet the laws of quantum mechanics say that information can't be destroyed. Physicists notice something peculiar. The amount of information a black hole can contain what we call its entropy, isn't proportional to its volume, as you might expect, but to its surface area. The boundary, not the inside, holds the secrets. This discovery led to a revolutionary idea, the holographic principle, which we'll explore more deeply soon. It suggests that the universe itself might be like a hologram, where the three-dimensional world we experience is actually a projection from information encoded on a two-dimensional surface. Gravity, in that sense, might just be geometry's way of keeping track of that information flow. But before we reach that idea, let's pause for a moment to appreciate the irony. The weakest of all forces, the one you can overcome just by lifting a cup of tea, is also the most universal. It governs the motion of galaxies, shapes the evolution of the cosmos, and yet remains the hardest to reconcile with the rest. The three other forces fade with distance. Gravity never does. Its reach is infinite, its patience eternal, and perhaps that's why it resists quantization. Gravity doesn't behave like a messenger. It behaves like a storyteller. It doesn't just transmit forces between particles, it dictates the very structure of existence. The others describe what happens inside the universe. Gravity describes where and when anything can happen at all. When you think about it that way, it's no wonder gravity sits apart. It's not a rebel, it's the foundation. To quantize it would be like trying to define the edge of a circle while standing inside it. The closer you look, the more the edge retreats, until you realize you were part of it all along. Even so, scientists haven't given up. The dream of unification, of bringing gravity back into the fold, still glows quietly at the heart of physics. Because somewhere, deep down, the universe doesn't seem like it should have two conflicting operating systems. There should be one code, one underlying pattern that makes both the cosmic and the quantum make sense together. And that search leads us next to one of the most ambitious and imaginative ideas ever conceived. A theory that dared to replace point-like particles with tiny vibrating strings, and in doing so claimed to unify every force, every particle, and perhaps even every possibility. It's an idea as musical as it is mathematical, one that promised beauty and found itself tangled in it. Our gentle exploration now turns to that daring vision, to the dream that the universe, at its core, might simply be a song played on the strings of existence. If the universe could be heard instead of seen, perhaps it would sound like a symphony. Deep, resonant, infinite. Every atom, every field, every breath of space would carry its own vibration. For centuries, scientists imagined matter as tiny points, hard, indivisible specks too small to see. But what if instead everything was strings? Not the kind that hang from a violin, but unimaginably small loops of energy, stretched and vibrating in patterns so delicate they give rise to everything. Light, gravity, even you. This was the daring idea that emerged in the 1970s, string theory. It began almost by accident as an attempt to describe the strong nuclear force that binds quarks inside protons and neutrons. The first equations worked better than expected, so well in fact that they revealed something strange. Hidden inside the math was a vibration with exactly the right properties to represent a graviton, the hypothetical quantum of gravity. It was as if nature had quietly slipped the missing note into the sheet music. The idea was electrifying. Maybe at the deepest level, all forces and particles, from photons to gluons to electrons, are just different harmonics of one underlying instrument. Imagine a single violin string. Pluck it softly, and you hear the fundamental note. Pluck it differently, and you hear overtones, higher pitches, same string. In the same way, physicists imagined that the different vibrations of a fundamental string could produce all known particles. The electron, the quark, the neutrino. Each could be one pattern among many. The universe would no longer be a collection of particles, but a composition of frequencies. For a moment, It seemed that the dream of unification had finally been realized. Here was a single framework that could include gravity, quantum mechanics, and all other forces at once. No infinities, no contradictions, just elegant equations singing in perfect harmony. But there was a catch. The math only worked if the universe had 10 dimensions, not 3 of space and 1 of time, but 6 hidden ones curled up so tightly we never noticed them. These compact dimensions were imagined to be microscopic loops folded inside every point of space, like threads in a woven fabric too fine to touch. Physicists gave them names: Calabi-Yau manifolds, intricate shapes that determine how strings vibrate. Change the shape, and you change the entire physics of that universe. The forces, the masses, even the number of particles. It was as if the universe had an instrument case full of violins, each tuned to a different cosmos. At first, this hidden complexity seemed enchanting. The extra dimensions offered possibilities, new ways to explain why our universe looks the way it does. But soon, the enchantment gave way to unease. There weren't just a few possible shapes. There were billions upon billions. Each one produced a different version of physics. This overwhelming variety became known as the string landscape, a vast field of potential universes, each with its own laws like pages in a cosmic library. Somewhere in that landscape might be our universe, but finding it was like trying to pick a single grain of sand from all the beaches on Earth. To some, this was thrilling, a glimpse of a deeper reality, a multiverse of possibilities. To others, it felt like failure disguised as freedom. If a theory can describe everything, it also risks predicting nothing. Without a way to choose which version corresponds to our world, string theory teetered on the edge between science and philosophy. Even so, the beauty of the mathematics was undeniable. The equations were consistent, elegant, and full of unexpected symmetries. They hinted at a unifying structure, something that made sense even beyond our imagination. Many physicists couldn't look away. As one of them once said, "We don't believe in string theory because it's right. We believe in it because it's too beautiful not to be." That beauty also carried a warning. History shows that nature often rewards elegance, but not always. Einstein's field equations are stunningly simple, but the universe they describe is full of chaos. The human brain loves patterns. It finds harmony comforting. But nature's definition of beauty might not be ours. Over the decades, the promise of string theory led to further surprises. The mathematics began to suggest that strings weren't the whole story. There might also be higher dimensional objects, surfaces and membranes, or brains for short, that could stretch across entire universes. Our own cosmos might even be one such brain floating in a higher dimensional space, with gravity leaking faintly between worlds like whispers through thin walls. And though no experiment has yet seen a string or a brain directly, they're far too small to probe, far beyond the reach of any microscope or collider. The theory has changed how we think about space-time itself. It showed that gravity and quantum mechanics could, in principle, coexist peacefully within a deeper geometry. Even if we can't test it yet, string theory has become a language for thinking about unification, a kind of poetry written in mathematics. To understand how delicate these strings are, imagine their scale. A single string is thought to be about 10 billion times smaller than an atom. So small that if a proton were the size of the solar system, the string would be no bigger than a tree. Their vibrations happen at frequencies far beyond what any human instrument could hear. If the universe is music, it's a melody played in a register we can only feel through its echoes, and those echoes are everywhere. The way black holes store information, the way entropy seems to scale with surface area instead of volume, the way quantum information might shape space-time. All of these ideas trace their lineage back to string theory. Even the holographic principle, which we'll explore soon, emerged from its shadow. Still, for all its elegance, string theory remains untested. Its beauty has become both its power and its burden. Decades of work have shown no experimental confirmation, no telltale vibrations, no extra dimensions, no supersymmetric partners that were once predicted to appear. The Large Hadron Collider searched tirelessly and found none. And so, the dream of a single elegant equation faded again, replaced by a quieter understanding. Perhaps beauty is not the same as truth. Yet even if string theory never becomes our final theory, its legacy endures. It taught us that unification may not mean simplicity, but connection, that the universe might be more like music than machinery. Every vibration, every tone, every resonance contributes to the grand composition we call reality. As we drift deeper into this story, the melody of string theory begins to shift. Its harmonies reveal a strange reflection, a discovery that changed not only physics, but our very notion of what space and information might be. It's a revelation that suggests the universe, in all its vastness, might actually be written on its own boundary, like a song encoded in the surface of silence itself. For a while, string theory seemed to promise everything. It offered a single framework that could hold all the known forces of nature, a dream Einstein himself had chased until his final days. It was elegant, mathematically consistent, and full of quiet symmetries that felt almost divine. But as the decades went by, that same beauty began to reveal its shadow. It's strange, isn't it? How something so perfect on paper can resist every attempt to meet reality. String theory, for all its harmony, became like a song too high for the human ear, haunting but out of reach. The more deeply physicists listened, the more they realized that this melody could be arranged in infinitely many ways. The problem came from those hidden extra dimensions. The theory required 6 of them beyond the familiar 4, 6 tiny directions curled up in shapes more intricate than any sculpture, each defining how the strings vibrate. Those shapes, the Calabi-Yau manifolds, can be folded, twisted and compacted in almost endless combinations. Each configuration creates a universe with its own laws, different forces, different constants, different forms of matter. At first, this seemed thrilling, the universe as an infinite garden of possibilities. But soon, the number of possible versions of reality grew beyond comprehension. Not dozens, not hundreds, but numbers so vast they defy the imagination. Perhaps a 1 followed by 500 zeros. A number so big that even if every atom in the universe tried to represent one of these possibilities, we'd still run out of atoms. Physicists began to call this dizzying collection the string landscape. Somewhere within that landscape must be our universe, the one with just the right laws for stars, chemistry, and consciousness to exist. But if there are so many universes allowed by the equations, how do we know which one we live in? And worse, if every version is possible, what does it mean to predict anything at all? A theory that can describe everything, without explaining why we get one specific outcome, risks describing nothing. To some, this was a profound turning point, a recognition that maybe physics itself was running into its natural limit. If every combination of dimensions could be real somewhere, perhaps our universe was simply one random note in a cosmic symphony. Others pushed back, arguing that science must aim for more than mere possibility. It must offer testable predictions. Without them, even the most beautiful equations become poetry untethered from the world. And yet, there were hints of order even in this apparent chaos. Some researchers proposed that not every shape, not every combination of dimensions could actually exist. There might be deep constraints, invisible rules governing which universes are allowed and which are forbidden. This idea evolved into what's now known as the Swampland program. In softer terms, imagine a great archipelago of islands floating in an endless sea. Each island represents a mathematically consistent universe, a vacuum where the equations of string theory hold perfectly. But surrounding them is a swamp of mirages, mathematical shapes that seem valid but collapse under closer scrutiny. The challenge is to map the islands, to separate the solid ground of real universes from the shimmering illusions that can never be. This search has led to bold conjectures, ideas about the limits of physics that, if proven, might reshape cosmology itself. For instance, some versions of string theory suggest that universes like ours, those with an ever-accelerating expansion, may not fit neatly into the framework at all. Others propose a subtle connection between the strength of gravity and the existence of other forces, as if every law of nature must remain delicately balanced on a single invisible scale. Even so, the larger problem remained. Beauty and predictability were no longer guaranteed companions. Physicists had fallen in love with string theory's elegance, but nature, it seemed, wasn't required to share their taste. Supersymmetry, one of string theory's cornerstones, had predicted that every known particle should have a heavier twin. These supersymmetric partners would help stabilize the mathematics and explain why gravity is so weak compared to other forces. But despite decades of searching, none have been found. The Large Hadron Collider, humanity's most powerful microscope, has seen no trace of them. That absence left many uneasy. For the first time in a century, physics didn't just lack answers. It seemed unsure what question to ask next. The dream of unification, once so close, began to feel like a mirage that retreats the nearer you approach. And yet, there's something quietly human in this struggle. We've always equated beauty with truth. From the proportions of Greek temples to the symmetry of snowflakes, we feel that elegance must mirror reality. But nature doesn't owe us beauty. Sometimes it hides truth inside chaos, symmetry inside imperfection. Even Einstein faced this tension. His equations of general relativity were breathtaking in their simplicity, and yet they led to predictions so strange that he doubted them himself. Expanding universes, warped time, black holes. It took decades before the evidence caught up. Perhaps physicists reasoned string theory would follow the same path, a long, silent wait for proof. But while the experiments have yet to confirm its details, string theory has changed the way we think. It gave rise to new mathematics, new dualities, and a new sense that gravity and quantum mechanics might not be enemies after all, just reflections of the same hidden harmony. Even its apparent failures have been fruitful. The idea of extra dimensions inspired theories about parallel universes, dark energy, and new kinds of symmetry. Its study of black holes led to deep insights about entropy and information, clues that would eventually blossom into the holographic principle, which reimagines the universe itself as a vast encoded surface. So perhaps beauty's trap isn't a prison after all, it's a challenge, a reminder that the universe is not obligated to satisfy our aesthetic instincts, but it often does anyway, just in ways we don't yet recognize. There's a quiet lesson here for both science and life. Sometimes the most meaningful discoveries come from ideas that never quite fit. The equations that fail can still reveal the shape of the truth behind them. String theory's greatest gift may not be its claim to be the final theory, but its insistence that elegance and curiosity can coexist with uncertainty. If we follow the thread a little further, that lesson takes us somewhere unexpected, into the strange mirror that string theory left behind, a reflection so powerful that it reshaped our understanding of space itself, showing that reality might be both deeper and thinner than we ever imagined. It's the beginning of a new idea, that everything inside the universe might, in some mysterious way, be written on its surface. And that's where our journey drifts next, toward the shimmering boundary of the cosmos, where gravity, information, and light meet, and where the universe begins to whisper its secrets through the language of holograms. Imagine standing before a mirror, watching your reflection move. You lift your hand, and the image lifts too, perfectly, silently, without delay. The reflection has no depth, yet somehow it carries every detail of you? What if, in some cosmic sense, the entire universe works like that mirror? What if everything we see as three-dimensional, every star, planet, and breath of air, is, at its deepest level, a reflection of information written on a distant surface? That, in essence, is the idea behind the holographic principle, one of the most profound and haunting revelations to come out of modern theoretical physics. It began as an attempt to solve one of the oldest riddles in science, the paradox of black holes and information. When Stephen Hawking showed in the 1970s that black holes aren't perfectly black, that they emit faint radiation due to quantum effects, a troubling question arose. If a black hole slowly evaporates, what happens to the information about everything that fell into it? In quantum mechanics, information can never truly be destroyed. But Hawking's calculations suggested it might vanish forever, erased from the universe. It was as if the cosmos had a leak, letting the bookkeeping of reality drift away into nothing. For decades, this mystery gnawed at physicists. Then, in the 1990s, a breakthrough came, not from observation, but from the strange overlapping worlds of string theory and quantum field theory. Juan Maldacena, a young physicist, proposed an astonishing correspondence, that a universe with gravity could be exactly equivalent to another universe without gravity, existing on its boundary. In softer terms, imagine a snow globe. Inside it there's a miniature world, curved space, swirling light, tiny particles moving about. That's the bulk, the universe with gravity. Now imagine the surface of the Earth, glass, smooth, flat, two-dimensional. The claim is that every event inside the snow globe can be fully described by information on that surface. Nothing is lost. Every flicker within has a matching note on the outer shell. This duality became known as ADS-CFT correspondence, a shorthand for anti-de Sitter space, a kind of curved universe, and conformal field theory, a type of quantum field theory on its edge. But you don't need to remember the words. All you need to know is that this was the first bridge between the two great languages of physics, the geometric smoothness of relativity and the quantum dance of probabilities. It was as though someone had found a translator that could make the poets of gravity and the mathematicians of quantum mechanics finally speak the same sentence. To get a feeling for what this means, think of a hologram on a credit card. It looks flat, yet when light hits it, you see the illusion of depth. Every tiny patch of the surface encodes the whole picture from a slightly different angle. Similarly, in the holographic view of the universe, the entire 3D reality we experience might be a projection, a deep illusion emerging from information stored on a two-dimensional boundary. This idea sounds fantastical, but it has deep mathematical and philosophical power. For one thing, it explains why the amount of information, or entropy, that a black hole can contain is proportional not to its volume, but to the area of its event horizon. The surface of the black hole, not the inside, holds its secrets. Every bit of information that falls in gets smeared across that surface like ink across parchment, never truly lost. Translated softly, if you imagine a black hole as a sphere, you might expect its informational capacity to grow with how much space it encloses, but the math says otherwise. It grows only with the size of its outer shell, like a diary that can record only as many secrets as you can write on its cover, no matter how thick its pages are. This revelation changed everything. It suggested that perhaps the same rule applies not just to black holes, but to the entire universe. Reality itself might be a kind of cosmic hologram, where the fabric of space and time is woven from information living on the edge. And the deeper physicists followed this idea, the more it seemed to explain. It tied together puzzles about quantum entanglement, gravity, and the flow of time. It gave rise to a new understanding of how information and geometry might be the same thing in disguise. Some even began to see space-time itself as an emergent phenomenon, a structure born from the invisible threads of quantum information. Where those threads are densely connected, space feels smooth. Where they loosen, space stretches. The universe, in this view, is not a fixed arena but a living web of relationships. You could picture it as a vast cosmic loom. The warp threads are quantum states, subtle patterns of possibility, and the weft threads are their correlations woven through entanglement. Together they form the fabric of space-time. Gravity, then, isn't something that bends that fabric. It is the bending, the texture that emerges from the way those threads twist together. This is what makes the holographic idea so powerful. It isn't just a metaphor, it's a blueprint for how two seemingly opposite worlds, the continuous geometry of Einstein and the discrete quanta of the quantum, could actually be the same story told in two languages. The universe inside the snow globe, with all its stars and motion, could be a projection of something much simpler written on the glass. Of course, this raises unsettling questions. If everything we perceive as depth and motion is really information on a distant boundary, then what does inside even mean? Are we living in the projection, or are we part of the surface itself? Does the concept of distance still matter when the entire universe might be a single, interwoven computation? These are questions without answers, at least for now. But even without full understanding, the holographic principle has reshaped how physicists think about reality. It's not just about equations, it's about the unity of opposites. How the deep and the shallow, the near and the far, might be reflections of the same truth. Perhaps the most comforting thing about it is that it restores balance. For all the apparent fragmentation of physics, the competing theories, the unending failures, holography offers a hint of wholeness. It says that nothing is ever truly lost. That even when information seems to vanish into the dark, the universe keeps a copy, written somewhere on its shimmering boundary. It's a beautiful thought, that existence might be like a cosmic memory, perfect and permanent, though we only ever see its flickering shadows. As we drift further into this story, those shadows will begin to take shape. We'll see how holography does more than explain black holes, how it reshapes the very foundations of quantum gravity and perhaps the story of space itself. Because if reality is a reflection, then understanding the mirror might be the closest we'll ever come to understanding the whole. If you close your eyes and imagine the universe, you might think of it as silent, a vast dark emptiness between stars. But in truth, space is not silent at all. It hums, it ripples, it sings in a voice so deep and faint that only the most patient instruments can hear it. Those vibrations are gravitational waves, tremors in the fabric of space-time itself, born from the most violent events in the cosmos, colliding black holes, merging neutron stars, dying suns. For a long time, these waves were only a dream. Einstein himself predicted them more than a century ago, but even he doubted they could ever be detected. The distortions they create are unimaginably small, smaller than a fraction of a proton's width. If you built a ruler the size of the Earth, a passing gravitational wave would stretch and squeeze it by less than the width of a single atom. And yet, in 2015, humanity heard them for the first time. Deep in the quiet countryside of Louisiana and Washington state, two enormous machines stood waiting. The twin detectors of the Laser Interferometer Gravitational Wave Observatory, known simply as LIGO. Each observatory had two tunnels shaped like an L, stretching 4 kilometers in each direction. At their ends, mirrors hung in perfect stillness. Laser beams bounced between those mirrors, travelling back and forth hundreds of times. For years, those beams traced paths of absolute silence, registering nothing but the breath of the Earth itself. Then, one September morning, the stillness broke. For just 0.2 of a second, the lasers flickered ever so slightly. A faint chirp, barely audible, appeared in the data. When converted into sound, it rose in pitch like a distant bird calling across a canyon. That was the moment the universe rang. Two black holes, each about 30 times the mass of the Sun, had spiraled together more than 1 billion light-years away. In their final embrace, they released an energy equivalent to several suns converted entirely into pure gravitational waves. And those waves, after travelling for more than 1 billion years through the dark, brushed gently against Earth. It's hard to overstate the quiet grandeur of that discovery. For the first time, we were not just looking at the universe, we were listening to it. The cosmos had spoken, and the voice matched the music predicted by Einstein's equations perfectly. The frequency, the rhythm, the fading tone, all of it aligned with the theory of general relativity. The universe, it seemed, had kept its word. Since then, other detectors have joined the listening. Virgo in Italy, Kagra in Japan, and soon LISA, a trio of satellites that will float in space, forming a triangle millions of kilometers wide. Together, they turn the Earth, and soon the solar system, into a colossal ear for the cosmos. Each detection is like a new note added to a growing cosmic score. One event from colliding black holes, another from merging neutron stars, another perhaps one day from something entirely unexpected. The waves themselves carry more than sound. They carry stories. From the way they stretch and squeeze space, scientists can tell how massive the merging objects were, how fast they spun, how far away they lived, even what the universe was like when their echoes began the journey. One of the most remarkable confirmations came in 2017, when both gravitational waves and light from the same event arrived together. Two neutron stars had collided, releasing not just a ripple in spacetime, but a flash of gamma rays and a spray of heavy elements, gold, platinum, and more, the stuff from which jewellery and planets are made. That moment showed, in exquisite harmony, how Einstein's smooth geometry and the shimmering world of quantum particles can meet. And yet, beneath that triumph lies a quiet unease, because every time general relativity passes a new test, it deepens a mystery. The theory works too well. Its predictions match reality so precisely that there seems no room for anything new to appear. And yet we know it cannot be the whole story. It breaks down inside black holes. It falters at the beginning of time. It cannot speak the language of quantum mechanics. So physicists find themselves in a strange place, listening to the universe, hearing exactly what they expected, and knowing that something must still be missing. Every perfect note conceals the silence between them, the subtle gaps where the unknown still hides. Perhaps that's the paradox of progress. The more clearly we understand the universe, the smaller the space becomes for mystery. And yet mystery never quite disappears. It just retreats to deeper places, waiting for quieter ears. Future detectors may help us find it. The upcoming LISA mission, a constellation of 3 spacecraft linked by laser beams, will orbit the Sun like a vast triangle. Instead of listening for short, sharp chirps, it will hear the slow bass tones of enormous black holes merging, their wavelengths millions of kilometers long. Imagine 3 mirrors drifting through space, held together only by light, listening for distortions thousands of times smaller than a human hair. Back on Earth, Kagra, built deep beneath the mountains of Japan, listens in the stillness of stone, protected from tremors and noise. Other ideas include Einstein telescope, a future European observatory buried underground, and Cosmic Explorer, an even larger version of LIGO. Each one aims not just to confirm Einstein again, but to push his theory to its breaking point, to listen so closely that even the smallest discord might be heard. It's a poetic kind of science. These detectors are, in a way, stethoscopes pressed to the chest of the cosmos. The universe doesn't shout its secrets, it hums them. And we, fragile and fleeting, have built instruments precise enough to hear them across billions of light years. There's something almost spiritual about that. that the same species once frightened by thunder now listens to the aftershocks of galaxies colliding. But even as we celebrate each detection, the real wonder lies not in confirmation, but in what we still can't hear. Between those grand cosmic notes there may be subtler vibrations, tiny quantum fluctuations of space-time itself, ripples so faint they blend with the noise of existence. Detecting them would mean glimpsing gravity's quantum side, a whisper from the place where Einstein's smooth stage dissolves into probability. And that is where the next frontier begins. Because if these great detectors are like ears listening to the thunder of the cosmos, then in quiet, laboratories all over the world, physicists are now building experiments to listen for the whispers, the faint quantum murmurs of gravity itself. As our story continues, we'll step away from the giant observatories and into rooms so small you could walk across them in 10 paces, where lasers trap dust grains and scientists try to measure the unmeasurable. These are the experiments that aim to bring the universe's most elusive force onto the tabletop, where we might, for the first time, see gravity behaving quantumly. In the grand halls of physics, discoveries often arrive with thunder. The roar of colliding stars, the pulse of lasers stretching across continents. But sometimes progress begins with a whisper. Picture a quiet laboratory, no galaxies, no cosmic fireworks, just a table no bigger than the one in your kitchen. On it, 2 tiny specks of dust hover in near-perfect stillness, separated by a few millimeters of air. Around them hums an orchestra of lasers, magnets, and silence. And in that silence, scientists wait to see whether gravity, the oldest, most familiar of all forces, can reveal its quantum heart. This is not science fiction. These are real experiments being built today, under projects known by initials like BMV or QGM, shorthand for quantum gravity entanglement experiments. The names sound technical, but their idea is astonishingly simple. If gravity is truly a quantum phenomenon, if it too obeys the strange probabilistic rules that govern everything else, then it should be able to create entanglement between 2 objects. Entanglement is one of quantum theory's most mysterious gifts. It means that 2 particles can become linked in such a way that what happens to one instantly affects the other, no matter how far apart they are. It's not a signal or a force in the ordinary sense. It's a kind of shared existence, as if 2 coins flipped on opposite sides of the universe could somehow agree on which face to show without exchanging a single word. So the question becomes, can gravity, the gentle curve of space-time itself, create that same link between 2 massive objects? In these tabletop experiments, scientists take 2 tiny spheres, each smaller than a grain of sand but still massive enough to feel gravity. They cool them down until they're nearly motionless, as close to absolute zero as our technology allows. Then they trap them with light or magnetic fields and let them float in the dark. No air currents, no vibrations, only the faint pull of their mutual gravity remains. If gravity is a classical force, smooth, continuous, like Einstein described, then the spheres will simply tug on each other a little, nothing more. But if gravity is quantum in nature, something subtler will happen. The spheres will become entangled. Their tiny gravitational fields will overlap, weaving their quantum states together. Each will enter a state of uncertainty, existing in 2 places at once, but their uncertainties will mirror each other. They will share their quantum confusion. If scientists can detect that entanglement, it would be the first direct evidence that gravity itself follows quantum rules, that space-time, like everything else, can exist in superposition. It would be one of the most profound discoveries in physics history. But detecting it is unimaginably difficult. The gravitational attraction between 2 such small objects is so weak, it makes a feather seem heavy. It's a pull a trillion times smaller than the force you feel from the earth beneath your feet. Any stray vibration, any tiny motion of an air molecule would overwhelm the signal. That's why these experiments must be performed in perfect stillness. vacuum chambers colder than interstellar space, isolated from every echo of the outside world. Some laboratories are already approaching this level of control. In England, Italy, and India, research teams are designing systems where micron-sized particles, spheres a few thousandths of a millimetre across, are cooled, levitated, and monitored by lasers that can measure displacements smaller than the width of an atomic nucleus. One such displacement, less than 1 part in a trillion of a metre, could reveal gravity's quantum whisper. To put that scale in perspective, imagine you're trying to detect a movement smaller than the thickness of a human hair, but you're measuring from across the Atlantic Ocean. That's the level of delicacy these experiments demand, and even if they succeed, the result will not be a fireworks display or a visible motion. It will be a subtle change in correlations, a pattern of coincidence between quantum states that shows the two particles are entangled. No one will see quantum gravity. They will infer it from the quiet logic of probabilities and interference patterns. The beauty of this approach is that it flips the usual direction of physics. For centuries we've looked outward, to stars, to galaxies, to black holes, just to test gravity. Now we're turning inward, creating little universes in glass boxes, asking if the same rules that govern atoms can bend space itself. And yet, these experiments are not just technical marvels, they carry a kind of philosophical weight. If gravity can create entanglement, it would mean that the geometry of space, the thing that defines distance, time, and causality, is not a smooth stage, but a web of quantum relationships. In that web, space itself becomes a network of correlations. Where the network is dense, geometry appears. Where it thins, space dissolves. On the other hand, if no entanglement is found, if gravity remains stubbornly classical even at these scales, that too would be revolutionary. It would mean that the universe operates on two separate layers, the quantum and the gravitational, forever distinct. It would force us to rethink what it means for information and matter to exist at all. Either result would teach us something profound. That's what makes these experiments so beautiful. They are tests of possibility, not just prediction. When you imagine them, those dust-like spheres suspended in darkness, exchanging the faintest of gravitational whispers, it feels almost poetic. Two tiny worlds, unaware of their significance, dancing to a rhythm older than time. Their pull is infinitesimal, but its meaning is cosmic. If you could magnify that moment, slow it down until you could watch each quantum fluctuation, you might see space-time itself shimmer, as if deciding between realities. Each experiment becomes a miniature universe, teetering between the classical and the quantum, asking quietly, "What are you really?" It's humbling to think that we may answer that question not with telescopes, but with tweezers and lasers, that the next great revolution in our understanding of gravity could come from something small enough to fit on a table. And as extraordinary as that is, it also feels fitting. The universe, after all, has always loved contrasts, the vast and the minute, the thunderous and the silent. The black holes that make space-time tremble also obey the same rules as the atoms in your fingertips. Perhaps we're only now beginning to see how they belong to the same song. As our story drifts forward, that song will change again, from whispers in laboratories to perfect synchrony in orbit. Because if these experiments test whether gravity can behave quantumly, others test whether gravity can ever fail to. They do it not by looking for what happens, but for what doesn't, for the perfect sameness of falling objects, the stubborn symmetry that nature refuses to break. And so, our next quiet step leads us from the humming labs of Earth to a silent satellite orbiting above it, where two tiny weights fall together side by side in the stillness of space, proving once again that gravity, even after all these centuries, still keeps its secrets close. High above the Earth, in the stillness where the air thins into nothing, a small satellite drifted through sunlight and shadow. Inside it were two tiny cylinders of metal, no bigger than pieces of chalk, falling freely side by side. They were falling not toward the Earth exactly, but with it, tracing its orbit, circling endlessly, locked in gravity's invisible embrace. Their quiet fall was the culmination of an idea older than science itself, that in the presence of gravity, everything falls the same way. This simple observation, sometimes called the equivalence principle, is the cornerstone of general relativity. It means that the gravitational pull on an object is proportional to its mass. So a feather and a hammer, if you remove the air resistance, fall at exactly the same rate. Astronauts on the Moon proved it dramatically in 1971, when one dropped those two objects side by side. They struck the lunar dust in perfect synchrony, as if echoing Einstein's insight across a silent world. But physics is rarely satisfied with beauty alone. Scientists have spent a century trying to break that perfect equality, to find even the smallest difference in how gravity acts on different forms of matter. Because if such a difference ever appeared, it would mean Einstein's picture of spacetime isn't the full story. It would open a door to new physics, perhaps even quantum gravity itself. Enter Microscope, a French satellite experiment launched in 2016, whose name stands for Microsatellite à traînée compensée pour l'observation du principe d'équivalence. You don't need to remember the words, only the mission. It was, quite literally, a test of falling. Inside the satellite were two test masses made of different materials, one of platinum, one of titanium. They floated inside a chamber with no air, shielded from the jostling of the spacecraft by an intricate system of electrostatic controls. As the satellite orbited the Earth, both masses fell together in microgravity. Sensitive sensors watched their motion with precision beyond imagination. If gravity treated them differently, even by the tiniest fraction, the satellite would detect a difference in their acceleration. And by tiny, physicists meant something almost beyond belief. They were looking for deviations smaller than 1 part in 1 quadrillion. That's a 1 followed by 15 zeros. To translate softly, if the platinum mass and the titanium mass had fallen at slightly different rates, even by the width of a human hair across the entire diameter of the Earth, the instruments would have noticed. But after years of measurement, no difference was found. The two objects fell in perfect unison, as if choreographed by an unseen hand. The result was both triumph and frustration. Triumph because it confirmed Einstein's principle with unprecedented precision. Frustration because the better the universe behaves, the harder it becomes to find where it misbehaves. Each time we strengthen our tests, gravity continues to whisper the same answer. I am consistent. The findings were so precise that physicists joked the next generation of experiments might need to test falling thoughts rather than falling objects. Still, new missions are already being planned. Microscope was only the beginning. Future satellites, like STEP, Satellite Test of the Equivalence Principle, aim to push the sensitivity another 100 times further, perhaps detecting a deviation at 1 part in 1,000,000 trillion. On Earth, experiments continue in vacuum towers, where researchers drop test masses from great heights inside evacuated shafts. Some use ultra-cold atoms as their falling objects, letting clouds of atoms rise and fall in perfect silence, like droplets of light in reverse gravity. Each atom is identical, each obeys the same rules, and so any difference between them, however small, would speak of new forces lurking beneath Einstein's calm surface. Why does this principle matter so deeply? Because it links geometry and motion, the very heart of general relativity. If everything falls the same way, then gravity can't be a force in the usual sense. It must be the curvature of space-time itself. Objects don't feel gravity. They simply follow the straightest possible path through a curved universe. But if that principle were ever to fail, if two materials fell differently, it would mean that gravity isn't purely geometry. Something else, something quantum or hidden, would be tugging at matter in ways our equations don't yet describe. there's a beautiful tension in that pursuit. On one hand, every confirmation of the equivalence principle feels like an act of reverence, the universe reaffirming its consistency, its quiet perfection. On the other hand, scientists are secretly hoping to find that first tiny crack, that whisper of a symmetry that could lead to something new. It's a bit like tuning a piano that has never once gone out of tune. You admire its steadiness, but part of you wants to hear a single imperfect note, just to remind you that music can change. Even null results, those that show nothing unexpected, are not empty. They set boundaries, trimming away the impossible, helping us understand where mystery hides. When microscope found no deviation, it didn't end the story, it sharpened it. It told us that if quantum gravity is out there, it must operate at scales even smaller, subtler, and more elusive than we had imagined. You can almost picture it. 2 feathers falling side by side in orbit, floating through sunlight and night, over oceans and continents, repeating the same graceful motion millions of times. Each fall says the same thing, yes, still equal. The beauty of that answer lies not in its novelty, but in its constancy. And yet, in that constancy, the universe keeps its secrets. Because perfect equality is not explanation, it's invitation. Each time we confirm Einstein's vision, we're reminded that even perfection has depth, that the surface calm of the cosmos hides a turbulence of unanswered questions below. As we continue listening, testing, and falling, our instruments reach the limits of precision, and our theories reach the edges of imagination. Still, the quest goes on, and just beyond these perfect experiments, beyond the feather's fall and the satellite's orbit, lies another kind of investigation, one that doesn't measure motion at all, but memory. It asks what happens when information falls into gravity's deepest well, and whether it ever truly escapes. In that question, we'll find both the most haunting paradox in modern physics, and perhaps a glimpse of how gravity and quantum mechanics might finally touch. Our quiet journey now drifts toward those mysteries, toward the black holes, that glow with impossible light, the horizons that hide information, and the discoveries that suggest even when the universe forgets, it remembers in whispers. If you look up at the night sky, you might think of it as quiet, a black canvas of stillness scattered with tiny lights. But if you could listen deeply enough, you'd hear a faint hiss, like the sound of wind over distant sand dunes. That whisper isn't noise, it's history. It's the afterglow of creation, the faint cosmic background left from the universe's first moments. And woven within that silence, if you listen carefully, are clues about the strangest conversation in all of physics, between gravity, information, and the mystery of black holes. Black holes have always been paradoxes made real. They begin as the most straightforward idea. When a massive star dies, its core collapses under its own gravity. If the mass is great enough, nothing can stop the collapse. Not pressure, not light, not time itself. Space folds inward, and what remains is a region so dense that its escape velocity exceeds the speed of light. The edge of that region is called the event horizon, the point of no return. To imagine it gently, picture a waterfall, but one that curves space-time instead of water. From a distance, you can see the flow, light, matter, everything rushing toward the edge. But once something crosses that invisible boundary, it's gone from view forever, carried into the depths. For a long time, black holes were thought to be perfect traps, cosmic vaults that could swallow matter, energy, and information without ever releasing them. But in the 1970s, Stephen Hawking made a discovery that changed that picture forever. By combining the ideas of quantum physics with the curved geometry of space-time, he showed that black holes aren't truly black, they glow. It happens because the vacuum of space isn't empty. Even in absolute darkness, tiny pairs of particles and antiparticles flicker into existence and then annihilate each other, like brief, ghostly bubbles rising and vanishing in a sea of nothing. Near the event horizon, one member of the pair can fall in while the other escapes. To an observer far away, it looks as though the black hole is radiating particles. That faint emission, now called Hawking radiation, means black holes slowly lose mass and, over unimaginable timescales, evaporate. The revelation was astonishing, a perfect fusion of Einstein's gravity and quantum uncertainty. But it came with a riddle that still haunts physics. If a black hole evaporates completely, what happens to the information about everything that fell inside? Quantum mechanics says that information can never be destroyed. It can be scrambled, hidden, transformed, but never truly lost. Yet, according to Hawking's calculation, the radiation emitted by the black hole carries no record of what was swallowed. It's as if the universe itself forgets. This became known as the black hole information paradox, and it split the scientific world. Some physicists argued that information must somehow leak out in the radiation, encoded so subtly we haven't yet understood how. Others suggested that quantum mechanics might need to bend, that perhaps at the very edge of time information can indeed vanish. For decades, the argument raged in seminars and late-night debates. But slowly, a new idea began to take shape, one that turned the paradox inside out. In recent years, physicists studying black holes within the framework of holography and quantum information found something remarkable. They discovered that the entropy, the measure of information associated with black holes, follows a pattern that rises and falls in time, a curve that resembles the act of breathing. At first, as the black hole radiates, its entropy grows. Information appears to be lost, but later it decreases again, suggesting that the missing information somehow re-emerges, woven into the radiation itself. This pattern is called the Page curve, named after the physicist Don Page. It was long believed that only a full theory of quantum gravity could reproduce it. But in 2020, new calculations using a technique called the Island formula did exactly that. They showed that when you account for subtle quantum connections between the black hole and the surrounding space, tiny correlations that bridge the event horizon, the information doesn't disappear at all. It just hides in plain sight. To describe it softly, imagine a diary thrown into a fire. The pages burn, the words vanish, the ashes scatter. But if you could track every spark, every puff of smoke, every photon of heat, you could, in principle, reconstruct the story. Nothing is truly lost. It's just translated into another language. That's what the new understanding of black holes suggests. When a black hole evaporates, the information about everything it swallowed isn't destroyed. It's gradually encoded in the outgoing radiation, bit by bit, like whispers carried away on the wind. The islands mentioned in the theory aren't literal places, but regions of space-time that behave as if the inside of the black hole is secretly entangled with the outside. The result is breathtaking. It implies that unitarity, the rule of quantum mechanics that preserves information, remains intact. Gravity and quantum theory, long thought to be incompatible, seem to agree on this essential truth. The universe keeps perfect records, even when it pretends to forget. There's a quiet poetry to that. It means that somewhere, encoded in the faint glow around black holes, lies the memory of everything that ever fell into them. Every atom, every photon, every whisper of starlight. Even when matter is torn apart, its information lingers, folded into the fabric of space-time like writing on a page too small for us to read. Of course, these insights come from theory, not experiment. We can't yet test the details. The radiation is far too weak to observe directly. But the consistency of the picture gives scientists something rare, a sense that, for once, the two great pillars, general relativity and quantum mechanics, might be telling the same story in different voices. And what a story it is. A tale where destruction becomes preservation, where death becomes translation and where failure becomes clarity. The very thing that once symbolized cosmic finality, the black hole, has become the universe's greatest teacher about renewal. Every paradox that seemed to divide physics has instead drawn its fields closer together. Even Hawking, before his passing, acknowledged that he might have been wrong, that the universe, in its quiet wisdom, never truly forgets. Perhaps that's the ultimate harmony, that nature keeps its balance not by choosing one theory over another, but by weaving them both into a larger tapestry. Gravity bends, quantum information flows, and somewhere between them meaning is preserved. As our story drifts onward, that tapestry will begin to unfold in even stranger ways. Because if space and time themselves can store memory, if information is the thread that holds the cosmos together, then maybe space and time are not as fundamental as they seem. Maybe they are the product of those threads, the shadow cast by connection itself. Our quiet journey now turns toward that possibility, to the notion that the universe's most familiar ingredients, space and time, might not be the foundation of reality at all, but its most beautiful illusion. Imagine the universe not as a vast emptiness filled with stars, but as a living web, a network of invisible threads that connect every particle, every quantum of light, every flicker of existence. Now imagine that what we call space isn't a stage stretched beneath those connections, but something born from them. That the fabric of the cosmos is not a fabric at all, but the pattern woven by the threads themselves. This is the startling, quietly beautiful idea of emergent space-time. It suggests that space and time, the most fundamental features of our experience, may not be fundamental after all. They may be emergent phenomena, like temperature or waves on water. And if that's true, then gravity too is not a basic force but a shadow, a whisper of something deeper, a reflection of the invisible relationships between the quantum elements of reality. To picture this, imagine a vast network of glowing points connected by lines, like stars in a constellation, but closer, more intricate. Each line represents quantum entanglement, that strange link that binds particles even when separated by light years. In some regions, the connections are dense and intricate. In others, they're sparse and loose. Where the network is tightly woven, the geometry feels solid. You could say there's more space there. Where it's thin, space stretches out. In this picture, geometry, the thing Einstein called spacetime curvature, is no longer fundamental. It's what emerges when enough quantum systems become entangled. In other words, where relationships are strong, distance shrinks. Where relationships fade, distance grows. It's a profound shift in perspective. Instead of thinking of the universe as things inside space, we start to think of space as what happens between things. One of the pioneers of this idea, Juan Maldacena, who first proposed the holographic duality, later inspired others to see geometry and entanglement as two sides of the same coin. The physicist Mark van Ramsdonk once described it in a simple but powerful way. If you decrease entanglement between two regions, space itself begins to tear apart. Entanglement doesn't live inside space, it creates space. You can imagine this like a piece of woven fabric. Pull a few threads out, and holes begin to form. Pull out enough, and the cloth falls apart entirely. The texture of space-time, it seems, depends on how tightly the universe is stitched together by quantum relationships. This idea, still young and speculative, has been shaped by insights from holography, quantum information, and even computer science. It treats the cosmos as something more like a computation than a construction, a process of encoding and decoding information that gives rise to what we perceive as reality. If that sounds abstract, let's soften it. Think of a forest. From afar, it looks like a continuous green blanket covering the land. But up close, you see that the forest isn't a single thing. It's a network of trees, roots, and air between them. The forest emerges from their connections. It isn't built from solid walls, it's defined by relationships, by the spaces between the trees as much as the trees themselves. In the same way, space-time might not be the wood of the universe, it might be its forest. The implications are staggering. It means that asking where is something might not make sense at the deepest level. Location could be nothing more than a shorthand for how strongly things are entangled. The closer two systems are correlated, the closer they appear in space. The weaker the connection, the farther apart they seem. It also means that the familiar distinction between matter and space might fade away. Matter doesn't sit in space-time, it participates in space-time's creation. Every particle, every quantum fluctuation, every field contributes to the web. The geometry of the cosmos isn't a stage we move through. It's the ever-changing shape of our relationships with everything else. Some researchers have tried to express this mathematically using something called tensor networks, diagrams that look like lattices or webs. Each node in the network represents a quantum system. Each line represents entanglement. By adjusting how the nodes connect, you can actually reproduce the geometry of curved space-time. These networks have become a new kind of a loom, weaving together gravity, quantum theory, and information. Even time in this view might be emergent. The flow we experience, from past to future, could arise from the growth of correlations, the gradual unfolding of the network structure. Time might not be a river we float through, but the feeling of the universe rearranging its own connections. This picture is so different from the classical one that it almost feels like poetry. It says that the universe is not a thing, but a conversation. That existence is a dialogue between quantum systems, and space-time is the rhythm of that dialogue. And yet, there's an odd familiarity in it. Haven't we always felt that distance is partly emotional? That closeness isn't only measured in meters, but in connection, in shared memory, in mutual awareness? The physics of emergent space-time seems to echo that same truth in a different key. The more deeply things are connected, the closer they become. The idea also hints at a new role for information. In the old picture, information was something stored in space, on hard drives, in brains, in stars. In this new picture, information is space, the flow of data through the universe. The web of entanglement and correlation is the very architecture of reality. The universe isn't built from matter and energy alone, but from meaning. There's still much we don't understand. These models work beautifully in simplified settings, universes that curve in neat ways, easier to handle mathematically. Our own universe, with its expansion and complexity, remains more mysterious. But even without a full map, we can sense the outline of something revolutionary. If space can emerge, then perhaps time can too. If time can emerge, then perhaps causality, the notion that one thing leads to another, is not absolute but approximate, an illusion that works only at large scales. And if all of that is true, then the universe might be more like a song than a sculpture, something constantly rewritten as it plays, coherence born from motion. In that sense, emergent space-time doesn't destroy wonder, it deepens it. It tells us that what feels solid, the ground beneath your feet, the air in your lungs, the stars above, is, at its core, made of connection, memory, and possibility. If we follow the thread a little further, we'll find other visions of this same idea, ones that attempt to quantize geometry directly, to treat space not as a smooth continuum, but as something grainy, pixelated, discrete. These theories don't describe the universe as woven fabric, but as a network of loops and knots, a kind of cosmic embroidery, where even the smallest area or volume comes in quantum steps. And so, our quiet journey now turns toward that vision, toward a world where geometry itself becomes atomic, where space is made of loops instead of lines, and where even emptiness has texture. If you could zoom into the universe far beyond what any microscope could ever see, past atoms, past quarks, past every vibration of string, what would you find? Would space still look smooth and continuous? Or would it begin to crumble into something grainy, like sand under a magnifying glass? That question sits at the heart of loop quantum gravity, one of the most daring attempts to understand space-time on its smallest scales. Where string theory imagines everything as tiny vibrating threads floating through space, loop quantum gravity, or LQG as physicists call it, imagines that space itself is made of threads. In this picture, the universe isn't a fabric stretched across a void, it's the weave itself, a kind of cosmic chainmail, built not of metal but of geometry. The idea sounds abstract, but it grows naturally out of Einstein's insight. If gravity is not a force but the curvature of space-time, then quantizing gravity means quantizing geometry, turning the smooth curves of Einstein's universe into something made of discrete units. It's like saying that the continuous line of a rainbow, when seen closely enough, might actually be made of tiny coloured beads. To imagine this, think of space as a vast network of interlocking loops, countless tiny rings woven together into a lattice. Each loop carries a small packet of area or volume, like a thread in a tapestry carrying a bit of colour. Where the loops meet, they form nodes, points of intersection that represent the atoms of space. These are not points in space, they are space. Between them there's no emptiness, because the loops themselves are what define distance and direction. The mathematical structures that describe this network are called spin networks. You can picture them as webs of light, shimmering in patterns that shift and evolve as the universe itself evolves. Each strand represents a quantum of geometry, the smallest possible surface, the smallest possible chunk of volume. They're unimaginably small. Each loop is thought to correspond to an area roughly 10 billion times smaller than an atom. At that scale, even time itself becomes granular, a sequence of tiny quantum ticks, rather than a smooth flow. To translate softly, if a second were stretched across the entire age of the universe, one of these quantum ticks would last less than a trillionth of a trillionth of a trillionth of that second. It's hard to visualize such smallness, so perhaps it's easier to think of sound. Just as a melody that seems smooth to the ear is made up of distinct notes, the space-time we move through, which feels perfectly continuous, may be made up of discrete quanta. The smoothness we perceive is an illusion born of scale, the same way a painting appears seamless from afar but reveals its brushstrokes up close, in loop, quantum gravity. These networks of loops don't live inside space-time. They are space-time. They form what's called a spin foam, a term that conjures the right image, a dynamic froth of bubbles, constantly forming, merging, and dissolving. Each bubble represents a quantum chunk of geometry changing in time. Together they describe how the universe evolves at its most fundamental level, not as a continuous film, but as a flipbook of geometric transitions. This approach has one remarkable advantage. It's background independent. That means it doesn't assume space and time exist beforehand. Instead, space and time emerge from the relationships between the loops themselves. It's a self-contained vision, where the fabric doesn't need a loom. The threads weave themselves. It's also deeply consistent with Einstein's spirit. General relativity taught us that space-time is not a stage but a player. Loop quantum gravity continues that revolution by saying the player is made of notes. Of course, translating that beauty into predictions is hard. The theory has had notable successes. For example, it predicts that the area and volume of any region can only take certain discrete values, like steps rather than slopes. It also offers possible explanations for what happens inside black holes and at the Big Bang, where classical relativity breaks down. In some models, the universe doesn't begin with a singularity, a point of infinite density, but with a bounce. The collapsing universe of one epoch rebounds into the expanding universe of the next, like a heartbeat that never truly stops. That picture is quietly poetic, a cosmos that breathes, not one that begins or ends. Still, challenges remain. Loop quantum gravity hasn't yet connected fully with the standard model of particles or the detailed predictions of quantum field theory. It tells us how space behaves at the smallest scales, but not yet how matter dances within it. The task of reconciling the granular geometry with the smoothness of our everyday experience remains unfinished, but perhaps that's fitting. Every theory, no matter how elegant, is a map drawn on the edge of the unknown. LQG may not be the final word, but it offers something precious. A reminder that even space itself could have texture, that what seems empty might be woven from invisible loops of meaning. There's a kind of humility in this vision. It replaces the infinite smoothness of classical physics with something finite and quantized. It says the universe doesn't need infinities to be magnificent. It's magnificent precisely because it's built from countable pieces, a grand mosaic whose beauty lies in its discreteness. And that mosaic extends beyond science. There's something comforting in the idea that the smallest scales of existence, far smaller than atoms, smaller even than light waves, might have structure, rhythm, and coherence. It means that nothing is truly continuous. Chaos, even the void, has design. In the end, loop quantum gravity and string theory, though different, may not be rivals but reflections of each other. One imagines everything as vibrations within space, the other imagines space as the vibration itself. Both are attempts to glimpse the architecture beneath the visible, to hear the hum behind the silence. Whether the universe is woven of strings or loops may not matter as much as what both reveal. That reality, for all its mystery, has pattern. It has order, and that in itself is enough to fill the mind with wonder. As we drift onward, that wonder turns once more toward the horizon, toward another approach that asks whether gravity itself might possess a kind of built-in balance. A theory that suggests the universe, rather than tearing apart into infinities, might steady itself naturally at high energies, like a river that grows calmer as it flows upstream. And so, our quiet exploration continues toward the idea of asymptotic safety, where gravity finds its own serenity amid the storm of the quantum world. There's a quiet irony in the way we study the universe. The deeper we go, the smaller, faster, hotter we push our theories, the more wildly they begin to behave. Equations that once flowed smoothly suddenly explode into infinities. Energy, curvature, density, all climb without limit. It's as though, at the edges of understanding, the mathematics begins to panic. But what if the universe itself doesn't? What if, hidden beneath those apparent infinities, there is a kind of built-in calm, a natural stability that prevents reality from ever truly spinning out of control? That is the hope behind one of the most intriguing ideas in modern physics, asymptotic safety. The phrase sounds technical, but its heart is simple. It suggests that even when we push our equations to the most extreme energies, to scales smaller than any particle we've ever measured, to temperatures higher than any star has ever reached, the behavior of gravity might not become chaotic. Instead, it might settle into a steady pattern, like a river that grows calm as it approaches its source. This concept first emerged in the late 1970s from the work of the German physicist Steven Weinberg. He proposed that perhaps gravity, when treated as a quantum field, doesn't need to be renormalizable in the traditional sense. That is, we might not need to clean up its infinities with ad hoc fixes. Maybe those infinities never appear, because the theory naturally guides itself to a fixed point, a kind of mathematical equilibrium where all the quantities stop growing, no matter how far upstream you go. To translate softly, imagine plotting the strength of gravity as you zoom into smaller and smaller scales. At first it changes wildly, climbing like a mountain trail, but as you reach the summit, the Planck scale, where space and time themselves begin to shimmer, nastasy, the path levels out, the view opens and the equations stop diverging. They become safe, finite, and well-behaved. That is what asymptotic safety means. The universe has a built-in speed limit for chaos. The beauty of this idea lies in its restraint. It doesn't demand extra dimensions, strings, or exotic particles. It simply asks whether the familiar theory of gravity might already contain its own remedy, whether the storm calms itself without outside intervention. Over the past few decades, physicists have used powerful computational tools, like the renormalization group, a mathematical microscope for studying how physical laws change with scale. To explore this possibility, their results are encouraging. In simulation after simulation, gravity seems to head toward that calm, fixed point. The exact details depend on the assumptions, but the trend is consistent. At high energies, the wild infinities soften. Instead of tearing space-time apart, the equations fold gently into predictability. It's as though gravity, for all its reputation as the wildest of forces, has the temperament of a monk, fierce on the surface, serene at its core. To imagine it more tangibly, picture a river seen from above. Downstream, it's full of eddies and turbulence, waves colliding, foam swirling, unpredictable and loud. That's the world of ordinary physics, where matter and energy interact chaotically. But trace the river backward, toward its source high in the mountains, and you find it narrowing, calming, slipping between stones in a steady trickle. The water isn't gone, it's simply organized. Asymptotic safety imagines gravity the same way. The closer you get to the beginning, the steadier the flow. If this picture is right, then space-time could be self-consistent all the way down. There would be no need for a new framework to rescue it. Quantum gravity would not be a replacement for Einstein's theory, but its natural continuation. The same melody carried into a higher octave. Yet, like many elegant ideas in physics, this one remains untested. Its evidence is mathematical, drawn from approximations and computer calculations. No experiment has yet confirmed it directly, though its quiet promise echoes through many corners of theoretical research. Some even suspect that the signatures of asymptotic safety might be hiding in the early universe, in the subtle fingerprints of cosmic inflation or the faint patterns of background radiation that fill the sky. If those traces could be found, they might show that gravity has indeed been safe since the beginning, that the universe's birth wasn't an explosion from infinity, but a transition through balance, guided by the same gentle mathematics that governs its present. There's something deeply comforting about that vision. It paints a cosmos not of chaos, but of self-awareness, a universe that, at every scale, knows how to keep itself from falling apart. It also redefines what failure means. When early attempts to quantize gravity produced infinities, physicists saw them as obstacles. Asymptotic safety turns them into clues, signals that point toward the system's hidden equilibrium. The infinities weren't mistakes. They were the edges of a map showing where calmness lies beyond. It's the same lesson found so often in science. What looks like divergence is often the beginning of deeper order. The failure of our old methods became the trailhead for a new way of thinking, and yet, the human side of this story might be even more beautiful than the physics. For all our equations and instruments, we're still explorers walking through fog, guided by intuition and metaphor as much as by proof. We imagine rivers, mountains, and threads, because the real landscape, the quantum fabric of reality, is beyond sight. We reach for images to steady ourselves in the dark. Perhaps that's why the notion of asymptotic safety feels so resonant. It's not just about gravity, it's about the possibility that the universe, even in its most extreme moments, is kind, that it contains a balance we can trust, even if we don't yet understand it. And if gravity can find calm within its own chaos, maybe so can we. After all, our minds are made of the same fabric, tiny ripples of matter and energy following the same silent equations. Maybe the serenity we seek in ourselves is just the echo of the universe remembering how to stay whole. As our quiet journey continues, we'll step beyond the laboratories and calculations into a gentler realm, where questions about physics begin to merge with questions about knowledge itself. Because at some point, the quest for a theory of everything becomes more than science. It becomes philosophy, a reflection on what it means to know, to imagine, and to be part of a universe that may never stop unfolding. There's a certain stillness that comes after the storm of discovery, when all the equations have been written, and yet the world remains silent in reply. Physicists, after a century of searching for a theory of everything, often find themselves not arguing about numbers anymore, but about meaning. What counts as knowing when the universe refuses to yield a final answer? In the mid-2010s, this quiet question became the centre of a very public debate. On one side stood George Ellis and Joe Silk, two physicists who argued that science must remain anchored to testability, that a theory only becomes science when it risks being proven wrong. On the other stood Richard Deward and others who proposed something new, that in the age of deep cosmology and untestable scales, perhaps we could evaluate a theory before experiments catch up. Their disagreement wasn't about data, it was about the soul of science itself. Ellis and Silk were the guardians of an older faith. That observation is the final court of truth. To them, a theory without evidence was like a story without witnesses. Dawid, meanwhile, spoke for the frontier, for the explorers who peer so far ahead that their telescopes haven't yet been built. He called his idea non-empirical theory assessment, a careful phrase for something quietly radical. What he meant, said softly, was this: when direct experiments become impossible, maybe we can still judge a theory by its coherence, its elegance, and its ability to explain everything we already know. Maybe the structure of reasoning itself can be evidence. If a theory fits the known world seamlessly and leaves no contradictions behind, perhaps that harmony counts for something. To some, that idea feels like a surrender. To others, it's a sign of maturity. After all, there are questions we can't test simply because of scale. We can't create a miniature universe in the lab to replay the Big Bang. We can't probe the centre of a black hole to see what happens beyond the horizon. Does that mean we stop thinking about them? Ellis and Silk would say no, that we must keep our imaginations tethered to observation, like a kite tied to the earth. Dawid would answer that imagination is the wind, that without it the kite will never rise. It's not a battle of right versus wrong, but of temperament, of how we choose to live with the unknown. Some minds find comfort in evidence, others in symmetry. Science at its best needs both. The rigour of proof and the freedom of wonder, the builder and the dreamer. To picture their difference, imagine two painters. One stands close to the canvas, studying every detail, each brushstroke tested against the light. The other steps back, squinting, searching for harmony in the whole. Both are trying to see truth, one through precision, the other through pattern. In practice, most science lies somewhere between them. Even in fields where data is scarce, intuition plays a role. Einstein once said that the truly valuable thing is intuition, that logic gives structure, but imagination gives flight. He himself relied on thought experiments, not laboratories, to bend the universe into new shapes. When he imagined elevators in free fall or light beams chasing themselves, he wasn't testing in the usual sense. He was listening to the rhythm of reason. Perhaps what we call knowing isn't a single act, but a duet, a dialogue between experience and expectation. When we look through a telescope, we see photons from distant stars, but to make sense of them, we need a theory, a narrative that tells us what those lights mean. Evidence gives us the notes, theory gives us the melody. Still, it's easy to forget how delicate that balance is. When mathematics grows too beautiful, we risk falling in love with the pattern more than the proof. When observation dominates, we risk losing imagination to precision. The art of science is keeping both alive, knowing when to measure and when to dream. Non-empirical theory assessment might sound abstract, but it's really a reflection of the human condition. We live in a world where much of what we love can't be measured. Beauty, courage, kindness, awe. And yet we know they are real. We sense their presence not through instruments but through coherence, the way they make the world feel more complete. Perhaps physics, at its outer edge, is learning a similar lesson. In ancient times, philosophers called this gnosis, a kind of knowing that comes not from touch, but from insight. The Greeks saw it in geometry, the early astronomers in the music of the spheres. When Copernicus imagined the Earth circling the Sun, he had no telescope, only the quiet conviction that the simpler story must be the truer one. Sometimes belief precedes proof, not as faith against reason, but as reason's lantern in the dark. It would be easy to say that modern physics has simply replaced one kind of faith with another, trading temples for laboratories, priests for peer reviewers, but that would miss the deeper continuity. Both are born from the same impulse, to find order in mystery, to trust that the universe, if we listen carefully enough, will make sense. Perhaps the real difference between science and faith lies not in certainty, but in willingness. Faith holds its truth forever. Science lets go when the evidence demands it. Science is the art of belief with open hands, and so the debate between Ellis Silk and Daweed isn't a battle of opposites, but a conversation between two necessary virtues, humility and daring. Humility reminds us to test, to question, to doubt. Daring reminds us to imagine beyond the data, to trust that the unseen may yet be discovered. In the quiet between their voices hums a deeper question, one that no theory can answer. Can any mind truly hold the whole universe? Our brains evolved to throw spears, to track seasons, to notice patterns of light in the trees. Now those same brains try to imagine 10 dimensions, quantum loops, and infinite geometries. We build machines that see what our eyes cannot, but the meaning still passes through us. Our limits are part of the story. And if we listen carefully, those limits don't sound like barriers. They sound like rhythm, like the breath between thoughts, the pause between notes. Maybe knowing doesn't mean holding everything at once. Maybe it means learning how to listen for what's beyond us and still find beauty in what we can reach. As our quiet journey drifts forward, that's where we turn next, to the horizon of the mind itself, and to the gentle recognition that every horizon moves as we approach it. Because knowing, like the universe, is never finished. It only expands. If you step outside on a clear night and look up, there's a moment when your mind stretches, when the scale of what you're seeing begins to outgrow the shape of your thoughts. The stars are so far away that even light, the fastest thing there is, takes years or centuries to reach us. And yet your eyes, evolved to track fruit and faces, are taking in the entire past of the universe. It's humbling to realize how much the human brain is doing its best with tools it never evolved to use. Our minds were built for warmth and survival. They were tuned to the rhythm of seasons, the pull of hunger, the sound of nearby water. We learned to throw stones, to count sheep, to see shapes in clouds. The universe, on the other hand, plays on scales that mock all of that. Scales of billions of years, trillions of kilometers, and energies so vast that even metaphor bends beneath them. It's no wonder we stumble when we try to understand it. We are creatures of mid-sized dimensions, trying to comprehend both the smallest particles and the largest galaxies. The philosopher and mathematician Kurt Gödel once proved a theorem that has haunted thinkers ever since. In any system powerful enough to describe itself, there will always be truths that can't be proven within that system. But here, let's take that idea gently, not as logic but as metaphor. Perhaps it means that every mind, even the universe's most brilliant, will always have boundaries, edges where certainty fades into wonder. We can illuminate much, but not everything. The light of reason always casts a shadow somewhere. It's easy to mistake those shadows for failure, but they're also what give the light its depth. Imagine a painter who discovers year after year new shades of blue. The more she paints, the more subtle her colours become, and the more she realises how many hues remain unseen. Knowledge is like that. Each discovery doesn't close the picture, it makes the canvas larger. Even our most fundamental perceptions betray us. We think of time as flowing, one moment pushing the next, but physics suggests it might not flow at all. We feel solid, but most of what makes us is empty space. We speak of particles as if they were little marbles, but they are waves, probabilities, relationships. Our intuitions are tiny rafts floating on an ocean of abstractions, and yet somehow they carry us farther than they should. That tension between what we evolved to perceive and what we've learned to imagine is where science lives. Every equation is a translation between our senses and the invisible. Every telescope and microscope is a prosthetic for curiosity, and every metaphor, from the fabric of space-time to the heartbeat of the universe, is a bridge we build between what is and what we can picture. The deeper we look, the stranger the view becomes. Quantum mechanics tells us that certainty is an illusion. Relativity tells us that time is personal, that what is now for you may not be now for someone else drifting near a black hole. Cosmology tells us that the universe might be infinite, or might curve back on itself, or might even be one bubble in an endless sea of universes. These aren't just puzzles of math, they are frontiers of imagination. To even think them is to stretch beyond what the human brain was designed for, and yet we do. That is perhaps the most remarkable thing of all. The universe evolved a species of ape clever enough to wonder where it came from. Somehow, matter learned to contemplate matter. The cosmos built an organ of thought, then gave it the audacity to question the cosmos itself. Maybe that's what it means to have a cognitive horizon. It's the line beyond which our minds cannot see clearly, the edge of comprehension. But unlike the horizon on Earth, this one moves as we walk toward it. Every time we learn something new, it recedes. We never reach the end because the act of seeing changes the landscape. There's something beautiful in that endless pursuit. If we ever did grasp the whole of reality, perhaps the story would end. There would be no mystery left to draw us forward, no reason to keep asking, to keep listening. But the universe, in its quiet generosity, always leaves a piece missing, a gap just large enough for curiosity to slip through. Even our limits may be part of a large design. Just as the human eye can't see ultraviolet light but still relies on it for the warmth of sunlight, maybe there are truths we'll never perceive directly that still shape our lives. We don't need to see everything to be part of it, and so we live, content in partial understanding guided by glimpses. Each generation extends the reach of thought, from Galileo's telescope to the quantum computer, from Newton's apple to the gravitational wave. We build tools to stretch our senses, but we also build metaphors to stretch our hearts. Science is not just data collection, it's the art of empathy with the universe, trying to feel what it feels like to be matter thinking about itself. Our limitations can even be comforting. They remind us that perfection is not required for meaning. You don't need to understand every law of nature to appreciate a sunset. You don't need to solve the universe to feel at home in it. The mystery is part of the belonging. So maybe the real wisdom isn't in conquering the unknown, but in learning to live gracefully beside it, to sit with not knowing and let it soften us. because when we accept our cognitive horizon, something else opens. Wonder. Wonder isn't ignorance, it's intimacy with mystery. It's the recognition that we are part of something vast, and that even our smallness is a kind of participation. In that light, every scientist, every thinker, every dreamer is like that painter of blues, adding colour to a canvas that will never be complete. And maybe that's the point. Knowledge grows not toward an end, but toward richness, toward deeper shades of truth that blend rather than replace each other. As we drift onward, we'll look at one last place where this richness hides, not in telescopes or thought experiments, but in the equations themselves. Because sometimes when we zoom in on the cold symbols of mathematics, we find unexpected beauty, shapes, symmetries and patterns that seem to hum with a meaning beyond language. Perhaps, even within the chaos of collisions and calculations, there's a geometry that whispers of unity, the hidden artistry of the cosmos. Somewhere between chaos and harmony lies the quiet beauty of mathematics, a place where numbers turn into shapes, and shapes begin to whisper secrets about the universe. You might imagine equations as cold and mechanical, but to the people who work with them, they are anything but. They're alive, flowing, curving, revealing glimpses of order within disorder. For much of the 20th century, physicists treated equations as tools, compact ways to describe motion, energy and forces. But lately, something curious has happened. Instead of solving equations line by line, scientists began to see them, to recognize that buried inside their symbols might be hidden geometries, elegant and unexpected. These discoveries didn't just make the math easier, they changed what understanding meant. Take the study of particle scattering, where two particles collide, interact and then fly apart. For decades, the math that described these collisions was mind-numbingly complicated, a forest of calculations stretching over dozens of pages. Each step worked, but the process felt mechanical, not meaningful. Then, a few decades ago, researchers noticed something remarkable. When they plotted the results of these calculations in the right way, the data didn't look random or messy. It formed a shape, a smooth multidimensional polyhedron. Its faces and edges corresponded perfectly to the possible outcomes of the particle interactions. It was as if the chaos of subatomic collisions had secretly been choreographed all along, each movement tracing part of an invisible crystal. They called this shape the amplituhedron, a name that sounds almost mythic but simply means the geometry of amplitudes. What's astonishing is that it allows physicists to calculate outcomes without using the traditional machinery of quantum field theory at all. The infinities that once plagued their equations vanish like mist. Translated softly, the amplituhedron suggests that the universe might not be built from little billiard balls colliding in space, but from relationships between points on a geometric structure that exists outside space itself. It's as if the laws of physics are drawn from a timeless diagram, and what we experience as motion and force are just its shadows flickering on the wall. To imagine it more simply, think of constellations. To the naked eye, the stars seem scattered at random, but draw a few lines between them and patterns emerge. Orion, Lyra, Cassiopeia. The connections are invented by us, yet they reveal something real about them, symmetry and rhythm we long to find in the night. The amplituhedron is like that, except the lines aren't human inventions. They're built into the mathematics itself, and this is not the only such revelation. Across the frontiers of theoretical physics, similar patterns are appearing. Scattering amplitudes, once thought to be chaotic, reveal perfect symmetries when re-expressed geometrically. The bootstrap method, which uses only consistency and symmetry to rebuild particle interactions from scratch, has rediscovered old results in new, astonishingly elegant ways. It's as though nature, beneath all the apparent mess, keeps sketching the same graceful curves. Some researchers have even begun to wonder whether space-time and energy are merely byproducts of these hidden geometries. instead of matter moving through space, maybe what we call motion is simply the unfolding of geometry itself, shapes changing in a timeless realm of possibility. We don't yet know what that realm is, or if it's something we can ever observe directly. But the fact that our equations seem to point toward it feels like hearing a melody through a closed door, faint but unmistakable. In a sense, this is the universe talking back. Every time our equations grow too complex, too ugly, something elegant emerges to restore balance. The history of physics is full of these moments. The way Maxwell's messy formulas collapsed into 4 perfect lines describing electromagnetism. The way Einstein's tangled algebra simplified into the serene curvature of spacetime. The way quantum mechanics, for all its strangeness, always finds order in probability. The amplitahedron and the new geometries like it are part of that same lineage. They remind us that complexity is often a disguise for simplicity, and that what feels chaotic may only be a shadow of a deeper harmony. If we take that idea seriously, it suggests something profound. Maybe beauty isn't just a coincidence in physics. Maybe it's a clue. The more deeply we search for understanding, the more elegance we find, as if the universe itself prefers grace over disorder. Of course, not everyone agrees. Some scientists warn that beauty can seduce, that we may mistake aesthetic pleasure for truth. But perhaps beauty in this context isn't decoration. It's coherence. It's the sense that everything fits, that the pieces resonate, like notes in a chord. When the equations sing in tune, we know we're closer to something real. You can think of it like listening to an orchestra tuning before a performance. At first it's just noise, scattered notes, discordant sounds. Then, gradually the tones align. A C resonates with an E, a G vibrates in sympathy, and for one brief moment the hall hums with perfect harmony. That's what it feels like when physicists glimpse one of these hidden geometries. It's not proof, it's resonance. The mathematics doesn't just describe reality, it dances with it. Even if we never find a final theory, these geometric revelations give us something precious, glimpses of connection. They show that the universe is not indifferent or random, but ordered in ways we can sense, even if we can't yet define them. They are reminders that, for all our limitations, the human mind is capable of touching patterns far older and grander than itself. Perhaps that's what the search for a theory of everything has always been about. Not possession of truth, but communion with it. The equations are not cages, they're invitations. Each one is a doorway into a world where structure and meaning meet. And maybe that's why, even after centuries of failures, physicists keep trying. Because every failure reveals a fragment of the larger geometry. Each discarded theory is a line on the growing constellation, a new point of light connecting what came before. The universe, it seems, rewards persistence with beauty. As our story drifts toward its closing chapters, that beauty becomes our compass. Because if all these patterns, holography, loops, amplituhedrons, entanglement, are fragments of a single larger truth, then the failure to unify them isn't a defeat, it's the texture of discovery itself. Perhaps the universe is telling us that elegance belongs not to the destination, but to the journey, that the act of searching is its own kind of harmony. And so, we follow that harmony one last time. From the patterns of equations to the patterns of thought, from geometry to gratitude, as we begin to understand what failure really means in a universe that never stops teaching. If you were to spread out the history of physics on a table, every equation, every failed idea, every half-completed proof, it would look less like a perfect map and more like a patchwork quilt. There would be seams, overlaps, blank spaces and stains from coffee cups left during late-night debates. But that quilt would still keep you warm. Because what we call failure in science has always been another name for discovery, a reminder that every wrong turn still moves us forward. It's tempting to see each broken theory as a dead end, a door that closes, But if you trace the story closely, you'll notice something softer. Every failed theory has given us something essential, a piece of understanding that the next generation would need. The path toward unity has always been built from mismatched stones, each one smoothed by the failures before it. General relativity, for instance, wasn't born in a vacuum. It came from Einstein's frustration with Newton's simplicity. Newton had imagined gravity as an invisible force that pulled things together, a clean, comforting idea that worked perfectly for apples and planets. But when Einstein looked closer, the equations began to blur. He saw that the old picture couldn't explain the bending of starlight or the strange precession of Mercury's orbit. The cracks in Newton's theory weren't flaws, they were invitations. They whispered that there was more geometry hiding in the motion of the heavens. So Einstein followed the gaps, and from them he built something luminous. General relativity gave us a new language for gravity, one where matter tells spacetime how to curve, and spacetime tells matter how to move. It didn't erase Newton, it completed him. The old equations still work for bridges and rockets, just as candlelight still works in a world that also has stars. Quantum mechanics followed a similar path. It too was born from confusion, from experiments that refused to obey the rules, light that behaved like particles one day, and waves the next, atoms that seemed to vanish and reappear. Out of that chaos came a new kind of logic. Probability itself became physical, uncertainty became law, and the very idea of knowing took on a new meaning. The failures that led to quantum theory gave us tools for an entirely new world, one where particles tunnel through walls, where energy comes in quanta, and where entanglement links distant things in invisible threads. Those failures didn't weaken science, they expanded its vocabulary. Then came the next generation, those who dreamed of unification. String theory, for all its challenges, gave us something the earlier frameworks never had, the idea of duality, that two seemingly opposite pictures could describe the same reality. What looked like particles from one perspective could look like vibrating strings from another. And from that came holography, the breathtaking realization that the universe might encode its volume on its boundary. Even the experiments that failed to find the predicted particles, like supersymmetric partners or extra dimensions, weren't wasted. They tightened the frame, refined the map, taught us where not to look. Failure is the compass that keeps exploration honest. Each null result isn't silence, it's guidance. And through it all, there's been another kind of success, one harder to quantify but perhaps more meaningful. Every time a theory collapses under the weight of new data, it humbles us. It reminds us that the universe doesn't owe us simplicity, and that certainty is often the enemy of curiosity. The discipline of doubt, of always questioning, always recalibrating, is what keeps science human. You can see it as a kind of conversation between our expectations and reality. Theories speak first, with elegance and optimism. The universe answers, not with applause or rejection, but with quiet correction. Together, they compose the rhythm of progress. Idea, test, revision, idea again. When you think of it that way, the failures of physics become like notes in a melody, each one resolving into the next, creating tension, release, and continuity. Einstein's equations didn't replace Newton's, they played the same tune in a higher key. Quantum theory didn't cancel classical mechanics, it added harmony. Even the ideas that didn't survive, like the ether or steady-state cosmology, or early versions of string theory, shaped the melody by showing what dissonance sounds like. The universe, it seems, teaches not just through answers, but through mistakes that clarify the questions. In that sense, physics is less like building a monument and more like exploring a coastline. Each map we draw shows a little more of the shape, but the fog never fully lifts. And every map that's later discarded still matters because its errors tell us where the cliffs are. As one physicist once said, Theories are like scaffolding. You climb them to build, then take them down. That's why the spirit of science has never been about certainty. It's about courage, the willingness to be wrong again and again in pursuit of something truer. It's about accepting that understanding isn't a possession, but a relationship, one that deepens through failure. In the soft light of hindsight, every discarded theory starts to look less like a mistake and more like a stepping stone. General relativity's success rests on Newton's framework. Quantum mechanics arose from the cracks in classical physics. Holography emerged from the gaps between geometry and information. Even the most speculative ideas, like loop quantum gravity or asymptotic safety, carry the torch forward, illuminating paths that may one day converge. Perhaps the universe doesn't want to be solved once and for all. Perhaps it prefers this rhythm, a dance of approximation, a dialogue without an ending. After all, perfection leaves no room for growth. It's the unfinished edges, the unresolved chords that keep us listening. Every failure, then, is a kind of kindness. The cosmos gently telling us, not yet, but keep going. Each time we stumble, we find a new angle, a clearer question, a more honest way to see. The path of science isn't paved with answers. It's lined with curiosity, humility, and the soft light of persistence. If you hold that thought for a moment, that failure is not the opposite of knowledge but its companion, then the long struggle for a theory of everything starts to feel different. It becomes less about closure and more about conversation. The universe speaks in puzzles, and we reply in hypotheses. Each side learns from the other. And so, as our quiet journey nears its final notes, we might look back not at what was solved, but at what was gained. Curvature, probability, duality, humility, each one a gift wrapped in the paper of a failed attempt. Each discarded map still teaching us the shape of the land. From here, the road ahead no longer needs to promise completion. It only needs to continue, gently, patiently, beautifully, toward a horizon that keeps receding, not to frustrate us, but to keep the story alive. Because maybe the real unification we've been searching for isn't in the equations at all. Maybe it's in us, in the way our endless trying mirrors the universe's endless becoming. And with that thought, the final session of our journey begins, a soft coda to everything we've learned, where failure and wonder meet, and where the search for unity becomes its own kind of peace. And so, after a long journey through equations and dreams, we find ourselves here, in the quiet after the questions. The instruments have fallen still, but their echoes remain, shimmering softly through the air. We've listened to the universe speak in gravity and light, in probability and geometry, in failures that were never truly failures. What we've learned is not a final truth, but a rhythm, a slow unfolding melody that stretches across time, played on the strings of curiosity. Every generation of thinkers has added a new note to that melody. Some sounded bold and clear, Newton's falling apple, Einstein's bending starlight, the quantum's shimmering uncertainty. Others were quieter, tentative, almost hesitant, a hunch that gravity might be emergent, that space-time could be holographic, that the universe might remember everything it forgets. None of them told the whole story, but together they formed something greater, a harmony of attempts. If there's one thread running through it all, it's that unity. The dream of a theory of everything may not be a destination we reach, but a direction we travel. The closer we get, the more we see how vast the landscape really is. Theories merge and divide, overlap and evolve, like rivers feeding an unseen ocean. And somewhere, in that mingling of successes and failures, lies the real beauty of science. Not the answers, but the act of listening. It's easy to forget that the universe doesn't owe us comprehension. It simply is. Yet somehow, we are part of it in such a way that we can ask about it. that matter itself has learned to wonder where it came from. When you think of it that way, every experiment, every blackboard full of symbols, every sleepless night of calculation is something astonishing, the universe thinking about itself. Perhaps that's why the search never truly ends, because the moment we understand one mystery, another one appears just beyond it, like a new horizon revealing itself as the fog lifts. Even now, after centuries of thought, we still stand at the shoreline, tracing patterns in the sand, listening for the tide to whisper back. But what if that never-ending nature of discovery isn't a flaw? What if incompleteness is the very feature that keeps the story alive? After all, a symphony that ends too perfectly leaves no reason to return to it. The beauty of the cosmos may lie precisely in its refusal to be finished. There's something deeply human in that realization. We too are unfinished, always learning, always revising, always trying to bring our inner worlds into harmony with the outer one. The same patience that guides a physicist through failed calculations is the patience that allows a heart to mend, a mind to grow, a civilization to dream. Failure, in the end, isn't the opposite of progress. It's the pulse of it, the beat that moves the melody forward. Every time an equation breaks, it leaves a silence for something new to enter. Every time an experiment disagrees, it reminds us that nature still has more to teach. The universe does not punish mistakes, it invites refinement. And maybe that's the quiet secret beneath all of physics, that perfection is not the goal, harmony is. When you look back at the long arc of discovery, from the first humans watching the stars to the gravitational waves trembling through space-time, you can see how the pieces connect, like constellations drawn between distant points. None of the lines are final, but they guide us through the night. Each failed theory adds a new star, and together they form the shape of our understanding, fragile, incomplete, and profoundly beautiful. The dream of a theory of everything was never really about having one equation to rule them all. It was about wanting to belong to something coherent, to know that the chaos of existence has structure, that our small lives fit within a larger design. Maybe the deeper truth is that the design is the reaching, that the search for unity is itself what unites us. Science, at its heart, is an act of faith, not in dogma, but in possibility. It's the faith that even when the path disappears, there will be something worth finding on the other side. It's the belief that the world, however mysterious, will respond to our curiosity with meaning. That's why physicists keep writing equations even when the chalk dust settles on 100 erased attempts. That's why experiments keep running, even when they find nothing new. Because each effort is an act of connection, a way of reaching out to the universe and saying, we're still listening. And the universe, in its quiet generosity, keeps answering. In gravity's whisper, in quantum shimmer, in the slow expansion of the night. If you listen closely, you can almost hear that answer. Not as words, but as a hum beneath everything. It's the sound of atoms vibrating, of galaxies spinning, of time itself breathing in and out. It's the sound of an unfinished symphony still being written, by us, with us, through us. And so, as our long, gentle journey comes to rest, we don't close the book. We simply turn another page. We leave the equations open, the telescopes pointed upward, the experiments running. Because the story of the universe isn't a story we observe, it's one we live inside. Perhaps one day, long after we're gone, another generation will find new harmonies, new shapes, new ways to listen. But even if they don't, even if the puzzle remains forever unsolved, there will still be wonder. And that wonder is enough. Because every failure, every silence, every unanswered question is the universe's way of inviting us to listen more carefully, to lean closer, to notice the subtle patterns in the noise, to fall in love again with the mystery of it all. And so, dear listener, whether your eyes are still open or already half closed, Thank you for walking through this quiet cosmos with me, for letting your thoughts drift among the stars, and for remembering that knowledge, like light, always travels, even when it seems to fade. The universe is unfinished, and so are we. But within that incompleteness lies something infinite, the soft hum of curiosity, the heartbeat of understanding. Sleep peacefully wherever and whenever you may be.